Welcome students, in this class we would be learning about Laplace transforms. Now, why Laplace transforms are very important. Laplace transforms help us to transform ordinary differential equations into algebraic equations. Now, why is this so much important? Now, algebraic equations are easy to solve. That is a simple fact. And Laplace transforms helps us in transforming ODE, ordinary differential equations, into algebraic equations. So that is the basic understanding that you should have before you could start to study Laplace transforms. Having mentioned it, now why Laplace transforms have become so much important? Of course, they were always important in the field of engineering. Specifically, they give it gives information on steady state as well as transient state. Now, if you are into engineering, you should be well aware of these two things, steady state and transient state. Now, this is in the engineering aspect. Now, you should be aware that we are living in a world where data sciences are now become pivotal foreground, and so is machine learning and artificial intelligence. So all these things are actually connected with data and with big data. It's imperative to understand now that Laplace transforms are used in data mining as well as in machine learning. So having mentioned this, it is necessary that you gain a greater understanding of the subject, Laplace transforms. So having mentioned that, without any further ado, I would like to start off. So first and foremost thing, what I would like to do is I would like to give you the definition. So what is needed? You have to know this, that whenever we are writing Laplace, it is represented by an L written in this fashion. Of course, there is no hard and fast rule to write L, but most of the time you would have seen people writing L like this. It's okay even if you write L in this fashion. It doesn't matter. What matters is the core of the substance. So Laplace transforms of a function. Now you would have seen that people writing t here. Now t is the variable that we are using. So have that in mind. As I mentioned to you, Laplace finds great applications in the field of engineering. So even if you are into, say, signal processing, and if you want to study a signal with respect to the frequency domain, then the most important point that you would be interested is to study the signal, whether it is smooth or not, over a period of time. So the study is always going to be over time. So that is the reason we have t being featured as the important variable inside Laplace transforms. So in other words, if you have anything else other than t, you can always treat it as a constant. So that is the understanding I wish to place in here. So having given you that, the definition for Laplace transform, L of f of t, is equal to integral 0 to infinity e raised to the power of negative s times t f of t times dt. So this is the important definition that you should have. Now clearly you can see that a function is actually changed into an integral. Now if you would have studied Riemann integral, a series is converted into an integral and then it is solved. So in this case, you got a function that is being converted into an integral. So that is a very important point that you will have to know. Okay, so having obtained this definition, this is all we need to gain a mastery over the subject. That's it. So the first and very important question that we will start is how to find the Laplace transform of e raised to the power t. Now what is this e raised to the power t? In this case, f of t is equal to e raised to the power t. So I would always suggest to write in the definition. So L of f of t is equal to integral 0 to infinity e raised to the power negative st f of t times dt. So as I mentioned to you, I'm not using the flower parenthesis, I'm using a square bracket. That is okay. So Therefore, if I were to write L of e raised to the power of at, then this is going to be integral 0 to infinity e raised to the power of negative st times e raised to the power at times dt. Now we know from mathematics a power m times a power n. This is from algebra, law of indices. We can write it as a raised to the power m positive n. So this is equal to integral 0 to infinity e raised to the power negative st positive at times dt. Now I can further rewrite this as integral 0 to infinity. Now this at is positive, so let me start with at and follow it by negative st times dt. I hope you are able to see that. So let me rewrite it probably over here. So this is equal to integral 0 to infinity e raised to the power of t is common actually, right? So I can take it out and write this as e raised to the power a negative s times t times dt. So this is what I wish to write it as. Now you have to know from the law of integration. Say suppose you have e raised to the power ax times dx. How do you integrate this? Say this is the rough side, right? So let me place it like that. Now if I were to use it by substitution, I would say a times x is equal to some t. Then when I differentiate, I get a times dx is equal to dt. Then I can write dx is equal to dt over a. This is the way I do it, right? So therefore I can rewrite this as e raised to the power ax is going to be t and dx is going to be dt over a. So this is going to be 1 over a e raised to the power t, which can be rewritten as 1 over a e raised to the power ax positive arbitrary constant c. So this is the usual way. Now all we need to do is just follow this usual way. So this is going to be equal to, when you integrate, you are going to get e raised to the power a negative s, right, times t divided by a negative s. So this is what you are going to be getting. Now the limits are 0 to infinity. So let us have that. Now what we can do is we can apply the limits. So I'm going to write that applying limits we get. So what do we get when you apply the limits? So this is equal to 1 over, now a negative s is constant, you take that out and you apply the upper limit. So this is going to be e raised to the power of a negative s times infinity followed by negative e raised to the power a negative s times 0. So this is what I've got. Now this is equal to 1 over a negative s. Now I want to make this as 0. Now when will this be equal to 0? Right? I want to completely remove it. Now the point is that when I say I want to make this as 0, I am meaning this entire component as 0. Now you got a value which is an exponent quantity here and you have it raised to the power of infinity. Of course there is some variable, say s or a minus s. Now the greater the values of this particular quantity, now as this a negative s goes up, this entire thing will be going up. So I got to make sure that this doesn't go up. So in other words, I want a negative s to be going down. The only possibility for that s should always be greater than a, right? Now if s is greater than a, definitely a negative s, this is actually going to be less than 0, right? Because just for example, just you take a to be equal to some 5 and s to be equal to some 5,000. So what happens when you subtract, from 5 you subtract 5,000? What do you get? You get negative 4,500. So that is definitely a lesser value, right? So as s increases or as s is huge, no matter what is the scale is, definitely a negative s is always going to be less than 0. So that would mean you can get rid of this term. So leaving you with 0, negative. Now this is going to be 0. This quantity exponent is going to be 0. So if that is being 0, you got something like this. So e raised to the power of 0 is going to give you 1. So you get a negative times this, and that would be negative of 1 over a negative s. Now I can rewrite this as 1 over s minus a with the condition that s is greater than a. So this you have to state this. This is imperative. Okay. So what is the final point you have arrived here? You have found out, therefore, Laplace transforms of the function e raised to the power at is equal to 1 over s negative a such that s is greater than a. So that is the solution to our first question. Students, we got this question. If f of t is equal to e raised to the power of negative at, with t being greater than equal to 0 and a is a constant, we are expected to compute the Laplace transform of this function f of t. And it is also given that s is greater than a. So this is very critical. This is very important that s is greater than a. It's given. So foremost, as I mentioned to you, we will define the definition for Laplace transform. So I'm going to start out by saying we know that L of f of t. Now you would have noticed that times I'm using flower parenthesis and times I'm using square parenthesis. It doesn't matter if you're using flower parentheses or square parentheses because it's just a convention. In some of the research articles, you would see that people don't even use these parentheses. They would use some other different conventions. So don't worry about it. So starting off, the Laplace transform of this is by definition given to be as integral 0 to infinity e raised to the power of negative s times t f of t times dt. Now given that f of t is equal to e raised to the power negative at, so that would mean we would now have this is equal to Laplace transforms of e raised to the power negative at is equal to integral 0 to infinity e raised to the power negative st times e raised to the power negative at times dt. I can rewrite this as integral 0 to infinity e raised to the power. I'm going to take negative sign out. That would give me s positive a times t times dt. Now if I were to integrate this, this is going to be e raised to the power negative of s positive a times t divided by negative of s positive a. The limits are 0 to infinity. Right? I've shown you how to integrate in the previous class. Now I'm substituting the upper limit. Now in fact I can take this out. So this is going to be 1 over s positive a. Of course there is a negative sign, so we place that. And I'm going to substitute the upper limit. So this is going to be e raised to the power negative of s positive a times infinity negative e raised to the power negative of s positive a times 0. Now clearly this is going to be 0, right? So we got this quantity which is going to be 1. So that means we got a negative 1 times a negative. So that would mean we got 1 over s positive a. So this is the solution for this particular question. So we can simply say therefore Laplace transforms of e raised to the power negative at is equal to 1 over s positive a. So we can square block that particular final answer. Now the question comes is, what if they ask you to find the Laplace transform of this function if a is equal to 0? What would you have to do? Now if a is equal to 0, then I'm giving you the solution. When a is equal to 0, this means f of t is equal to e raised to the power negative 0 times t, which is equal to 1. Right? This is what you have to integrate. So therefore the Laplace transforms of f of t is equal to a is equal to 0. So this is going to be, in place of a you substitute 0. So that's going to be 1 over s. So this is the final solution. So simple. We have not even integrated any quantities at all. All that we did is substitute the value of a into the outcome. So that is the solution for this question. Students, we will move on to the next question. Students, we are given this question. Find the imaginary part and the real part of Laplace transforms of e raised to the power I phi t. Now this can be easily solved because of the fact that we know that Laplace transform of e raised to the power at is equal to 1 over s negative a with s greater than a. So we know this. Now this would mean therefore Laplace transforms of e raised to the power I phi t is equal to 1 over s negative I times phi where s is greater than phi. So this is what we've got. Now we are expected to find the real part and the imaginary part. So that would mean, so let me use this space here. So this is equal to 1 over s negative, and I prefer to write it as 5i. Okay, this is s. Now I will be conjugate multiplying. So this is going to be s positive 5 times I divided by s positive 5 times I. So this is equal to s positive 5 times I divided by, now this is a negative b. Now there is a formula you have to know. This is, let me use the space here. Now a negative b multiplied with a positive b from algebra as a squared positive b, a squared negative b squared, right? Now if you have a negative ib multiplied with a positive ib, then the formula is a squared positive b squared. Okay, so I have that in mind. So if I were to multiply these two things, this is going to be s squared positive 5 squared, which is equal to s positive 5i divided by s squared positive 25. So this is what I've got. Now this can be rewritten as s over s squared positive 25 positive 5i over s squared positive 25. Now they want the real and imaginary part. So therefore the real part is equal to s over s squared positive 25, and the imaginary part is 5 over s squared positive 25. This is the final answer to this question, students. We will move on to the next problem. Given this question, f of t is equal to cos at for t greater than or equal to 0, and a is a constant. We are expected to find the Laplace transform of f of t. Now, foremost, we would have to use the Euler's representation for cos at. So we know that cos at is e raised to the power I times at positive e raised to the power negative I times at divided by 2. Now we also know that Laplace transform of e raised to the power I times at is equal to, now just refer to the previous question, we got Laplace transform of e raised to the power I times 5t. So this is what we have got. So I can safely use this over here. So it's going to be s positive of, I'm going to write it as I times a. It's up to you whether you write it as a times I or I times a. It's fine. So this is going to be s squared positive a squared. Right? Now, instead of positive IAT, if we were to be given negative IAT, how would that work out? What we have to do? It is going to be simple. Now, if you want, you can resubstitute and revert it using this, but I would prefer to show to you what happens if you were to be given e raised to the power negative I times at. So we can do that. Now, I will be using this Laplace transform. We know that Laplace transform of e raised to the power of negative at is equal to 1 over s positive a. So this would imply the Laplace transform of e raised to the power of negative, we got ia t. So in place of a, I've got an ia. So that would be equal to 1 over s positive ia. So this is what we've got. Now if I were to rewrite this, I can rewrite this with conjugate multiplication. So that would mean I get s negative I times a divided by s negative I times a. So this is going to be s negative I times a divided by s squared positive a squared. So that is what we have got. So I just want to have this as a rough column so that you will be in a position to understand this. So let us continue this. So we also know that L of e raised to the power of IAT is this, and L of e raised to the power negative IAT is equal to s negative of IA divided by S squared positive A squared. Okay. Now the question comes is, we are expected to find the Laplace transform of cos AT, which is equal to the Laplace transform of e raised to the power IAT positive e raised to the power negative IAT divided by 2. 2 has got no significance with reference to the operator L, so I'm going to take that out and I'm going to rewrite it like this. So we got a Laplace transform of e raised to the power IAT positive Laplace transform of e raised to the power negative IAT. So this is equal to 1 over 2 of this one. We need to substitute this, so this is going to be S positive IA divided by S squared positive A squared followed by this quantity S negative IA divided by S squared positive A squared. I can rewrite this with real and imaginary part. So this is going to be S divided by S squared positive A squared followed by positive IA divided by S squared positive A squared followed by positive this quantity real part S over S squared positive A squared negative I times A divided by S squared positive A squared. So you can cancel these imaginary parts, so that is going to be equal to half times, so half times of S over S squared positive A squared and S over S squared positive A squared. So you add them both, so that's going to be 2 times S over S squared positive A squared. You got a 2 here, you can cancel it, giving you S over S squared positive A squared. So you have a very important result. Laplace transform of cos AT is equal to S over S squared positive A squared. This is very important result. Students, we are given this question. Using the Laplace transforms of e raised to the power IAT, find the Laplace transform of sin AT. Now I'm going to use the Euler's formula. So this is something that we will have to be using periodically when we are dealing with E and Laplace transforms. So we know that e raised to the power IAT cos AT positive I times sin AT. So this is the expression that connects E with sine and cos. Now we also know that Laplace transform of e raised to the power. Now I showed you an illustration with I phi t. Now instead of phi, I'm just going to be using a there. So this would be equal to S positive I times A divided by S squared positive A squared. You can just go back to the past lesson which I just illustrated with A being phi there, and you can check it out. This would be the same outcome. The only thing that in that question the A would be replaced with phi. So this is what we have got. Now we also know that Laplace transform of cos AT is equal to, I just showed you this, S over S squared positive A squared. Now having this information, let us apply Laplace transform to 1. So I would state it, taking Laplace transforms on both sides of 1, we get, so what do we get? We get Laplace transform of e raised to the power IAT is equal to Laplace transform of cos AT positive I times sin AT. Now Laplace transform of a sum is equal to sum of Laplace transform. So this is equal to L of cos AT. Of course you can have the flower parenthesis, and Laplace transform of I times sin AT. So this is what you got. Now I can rewrite this as Laplace transform of cos AT. I don't want this imaginary quantity. In fact, I don't want this I. I'm taking I out. So it's going to be L of sine AT. So this is what we have got. On the left, we got Laplace transform of e raised to the power of IAT. So let me write that down. Okay. So now using the Laplace transforms that we have got, we will now have the left side is going to be this quantity. So let me write that down. So S positive I times A over S squared positive A squared, and the right side L of cos AT is going to be S over S squared positive A squared positive I times, this is what we need, L of sine AT. Right? Now I'm going to split this quantity as S over S squared positive A squared and I times of A over S squared positive A squared is equal to S over S squared positive A squared positive I times Laplace transform of sine AT. So this is what I got. Now equating the real and imaginary part. In fact, I don't need to equate the real part. I can simply say equating the imaginary part. We get. So what happens in the imaginary part? You got A over S squared positive A squared. On the right side, you got L of sine of AT. This is what you've got, right? So what does this mean? This means Laplace transform of sine AT is equal to A over S squared positive A squared. So this is the final answer. Now we have done this question from the information of Laplace transform of e raised to the power IAT, and with this formula that we have got. Of course, you don't have to do it in this fashion, but this is what the question wants. The question wants you to use these informations. Of course, by directly employing Euler's formula to sine AT, we can also extract this. So I have given you a very important transform here, Laplace transform for sine AT, and this is very important, and it is imperative that you have this at the corner of your mind. Students, we are given this question. The Laplace transform of a function f of t is as follows. F of s, this is capital F of s, which is equal to L of f of t, which is equal to integral 0 to infinity e raised to the power negative st times f of t times dt. Apply Leadness Rule by differentiating under the integral sign to obtain. So we are expected to obtain this. This is a very important result. So having mentioned that, let us consider capital F dash of s. Now what is capital F dash of s? This is nothing but d over ds of capital F of s. But what is capital F of s? This is nothing but d over ds of, it is given to be as Laplace transform of f of t. So let me write that down. But what is Laplace transform of f of t? This is equal to, this quantity is going to be integral 0 to infinity. I need to place e raised to the power negative st times f of t times dt. So let me place the entire component in flower parenthesis. Now I need to pull in this d over ds because I need to operate this e raised to the power negative st using this operator d over ds. But there is an issue. We got two variables. One is s and the other is t. So that means we need to only perform this operation as a partial derivative. In other words, the total derivative d over ds, when it goes inside the integral sign, it becomes a partial differentiation. So that is equal to, I'm going to place the integrals in sign, integral 0 to infinity. I'm pulling in the differential operator d over ds, it becomes partial operator, in other words dou over dou s. So now I need to place in the quantity e raised to the power negative st times f of t times, of course you need to have the differential. So this is what has to be differentiated. This is what we've got. We got to differentiate e raised to the power negative st. Now when we differentiate, we are going to get e raised to the power negative st, but the coefficient of s is negative t. So I will have to multiply that negative t with this quantity e raised to the power negative st. So that is very critical. So let me rewrite that down. So therefore, we got integral 0 to infinity dou over dou s of e raised to the power negative st times f of t times dt. When we differentiate, this is going to produce me integral, of course, integral 0 to infinity has to be maintained. So we are differentiating this. So this is going to be e raised to the power negative st along with the component negative t, because that is the coefficient of coefficient of s. So I need to place negative t there. So that is done, and then we got f of t there. So retain f of t as it is, and then we've got a dt there. So let me place all this in a square parenthesis, and I've got a dt there. Let me retain the dt. Now I can take the negative sign out, so it's going to be negative integral 0 to infinity e raised to the power negative st times f of t times dt. Of course, on the left we started with f dash of s, and then we stated this is nothing but d over ds of f of s. So this is what we've got, right? Now our requirement is to connect f dash of s with the transform here. Okay, so how are we? Of course, I need to place this t there, so that t has to be placed. So if I don't place the t, that's incorrect. So now what I want to do is I would want to draw your attention to what we have known by the definition of Laplace transforms. So we know that Laplace transform of f of t is equal to integral 0 to infinity e raised to the power negative st. This is the definition given in the question, f of t times dt, right? So now if I were to include a t inside, if a t comes into play, so this is going to be equal to, this component can now be rewritten as Laplace transform of t times f of t. And on the left hand side we got f dash of s. But our intention is to show the following. So I'm going to move this negative sign onto the left. So that would mean I would have a negative sign here, positive sign here. So rewriting, we get Laplace transform of t times f of t is equal to negative f dash of s. This is what is the result, and this is achieved. Hence the result. Students, we are asked to compute the Laplace transform of t times e raised to the power negative at. Now we will be using this result. We know that the Laplace transform of t times f of t is equal to negative f dash of s. As I mentioned to you, this result will be used on and on and on. Now we also know that f of s, which is nothing but the Laplace transform of f of t, is equal to integral 0 to infinity e raised to the power of negative st times f of t times dt. We know this. Now what are we going to do is we would be using these important definitions. So let's get started. So from the question we know that f of t is equal to e raised to the power negative at. So this would mean f of s is equal to Laplace transform of f of t, which is equal to Laplace transform of e raised to the power negative at, which we all know from the previous illustrations, s 1 over s positive a. So this is going to be my f of s. Now we are expected to obtain the differential of this quantity. So we will be using, this is my rough column, d of u over v, which is nothing but v times u dash minus u times v dash divided by v squared. So if you were to differentiate 1 over s positive a, this is going to be s positive a times differentiation of 1, that's 0, negative 1 times differentiation of s positive a. Now actually we are differentiating this with reference to s. So this will give me 1 divided by s positive a raised to the power 2. That's going to be negative 1 over s positive a raised to the power 2. So this is the differentiation. Of course it's d over ds. So f dash of s, therefore f dash of s is going to give me negative 1 over s positive a raised to the power 2. So hence, let us rewrite the final solution. Hence, Laplace transform of t times e raised to the power negative at is equal to negative of f dash of s, which is nothing but negative 1 over s positive a raised to the power 2, which is equal to positive 1 over s positive a raised to the power 2. This is the final answer to this question. Students, we are given this question, we are expected to find the Laplace transform of t raised to the power n. It is just t raised to the power n, you don't have any additional f of t. So let us see how we can achieve the solution for this question. So for this, what we would do is we will use the Laplace transform of e raised to the power at. So this is going to be equal to 1 over s negative a. Of course, s is greater than a, which is greater than 0. Now, you all would have known this series, e raised to the power x, which can be actually written as a summed up series. And that would be 1 positive x over 1 factorial, positive x squared over 2 factorial, positive x power 3 over 3 factorial, plus etc. Now this entire series can be written using the summation x to the power n divided by n factorial, when n is equal to 0 to infinity, because when n is equal to 0 you get 0 factorial, which is equal to 1, and x power 0 is 1, and that will produce the first term, and so on and so forth. So using this, hence we can write e raised to the power at to be as sigma 0 to infinity. In place of x, I've got at, so this is going to be at raised to the power n divided by n factorial. Now I can rewrite this as sigma n is equal to 0 to infinity a raised to the power n t raised to the power n divided by n factorial. Now I want to rewrite this as sigma n is equal to 0 to infinity t raised to the power n divided by n factorial times a raised to the power n. Now why am I writing like this with t raised to the power n? Because I'm trying to achieve the requirement, that's a reason. So this is one side, okay? Now moving on, we have seen 1 over s minus a on the right hand side. So what I wish to do is, I would like to draw your attention to this popular series 1 over 1 negative x. I can rewrite this as 1 negative x raised to the power negative 1, which is going to give me 1 positive x squared, positive x power 3, positive etc. It's a popular series. So this is rewritten as x to the power n with the sigma, and n is starting from 0 to infinity. The requirement here is modulus of x should be less than 1. So we are going to use this series over here. So hence 1 over s negative a, I'm going to be rewriting this as 1 over, I'm taking s out, so I will get 1 negative a over s. I can rewrite this as 1 over s. I can move this up. It's going to be 1 negative a over s raised to the power negative 1. In place of x, I've got a over s. Now clearly we know that s is greater than a. So this would mean a over s, modulus of a over s would be less than 1. So this would mean I can rewrite this entire thing as sigma a over s raised to the power n. Of course, n going from 0 to infinity. Right. Now I can still further rewrite this as 1 over s sigma a raised to the power n divided by s raised to the power n. Now I can add these two quantities and rewrite this as sigma. I can push the s inside, so that is going to be a raised to the power n divided by s raised to the power n positive 1. N is stretching from 0 to infinity. So we've got this for the right side. So hence, what I'm going to write, hence Laplace transform of e raised to the power of at, okay, is equal to 1 over s negative a now becomes, so Laplace transforms of e raised to the power at is sigma n is equal to 0 to infinity t raised to the power n divided by n factorial times a raised to the power n is equal to 1 over s negative a is sigma a raised to the power n divided by s raised to the power n positive 1, n is equal to 0 to infinity. So we've got these two terms like this. Now what I wish to do is I would like to pull in the Laplace transform and take away the terms which aren't matters to me. Now remember, in Laplace transform the only variable that counts or matters to us is t. I mentioned to you in the beginning of this class. So I can rewrite this as sigma. I'm actually bringing this n factorial out. I'm pulling the Laplace transform L into, so this is going to be t raised to the power n. And I can have this a power n outside. So this is what I've got. Now you can place this entire thing in a curl parenthesis. So this is equal to sigma a raised to the power n divided by s raised to the power n positive 1. N is equal to 0 to infinity. So you got a term like this. Now our objective is to reach out, extract Laplace transform of t power n. Now if you were to observe this, this is actually an infinite series. N is equal to 0 to infinity, and on the right hand side you have infinite series. And if you were to clearly observe this, we have got two infinite series connected by an equal to sign. So the underlying point is these two infinite series can only be equal if the coefficients of these terms are equal. So that would mean, this would mean the Laplace transform of t power n with 1 over n factorial, that is actually the coefficient with this infinite series, the term of a raised to the power n, that should be equal to this quantity 1 over s raised to the power of n positive 1. So this is what this should be true. In other words, since this is what we have got, and the only way that this can be true is this should be true. So this would mean the Laplace transform of t raised to the power n is equal to, move this n factorial to the right, so that's going to be n factorial divided by s raised to the power n positive 1. So this is the very important result that we will have to have it in the corner of our mind. Students, we are expected to obtain the Laplace transform of Shin, its hyperbolic function of 6t. Now before we could obtain this, let us find the Laplace transform of Shin for a general quantity. So that would mean we will have to first get the Laplace transform of Shin, say at. So this would mean that no matter if they give you 6 or 61 or 6,000 or 6 million, you will be able to use this formula. So that is my objective. Now I would like to draw your attention to this all important formula of Shin theta. Now Shin of any function that you are given can be represented. So this is going to be e raised to the power of positive theta negative e raised to the power of negative theta divided by 2. Now just out of consistent interest, what if they give you say Shin of 2 theta? So in this case, this can be rewritten as e raised to the power of 2 theta negative e raised to the power of negative 2 theta divided by 2. I can further rewrite this as e raised to the power of theta negative e raised to the power of negative theta. I'm just writing the numerator, right? So this is further, this has to be multiplied by e raised to the power theta negative. In fact, this, if you are retaining as negative, this will become positive. But I'll start with a positive sign and I will have this as a negative sign. Okay, so if I were to multiply this, say I'm using the algebraic formula a positive b multiplied with a negative b, this is going to give me a squared negative b squared, right? So if I were to use this formula, this is going to give me e raised to the power 2 theta negative e raised to the power of negative 2 theta. That is exactly what we would be arriving at. Of course, you got a 2 there, so I'm placing a 2 here. Now, this is for the denominator. So let me just stretch the denominator line. So this is what I have got. Now the question is, if I were to multiply the numerator and the denominator by 2, I'm multiplying the numerator by 2, I'm multiplying the denominator by 2, then this can be rewritten as 2 times of, so let me write this down like this, e raised to the power theta positive e raised to the power negative theta divided by 2, and e raised to the power of theta followed by negative sign and e raised to the power negative theta divided by 2. Now this is clearly Shin theta. So let me have this 2 times of e raised to the power theta positive e raised to the power negative theta over 2. This quantity is Shin theta. Place it. Now what is this quantity? What should be this quantity? Yes, you guessed it correct. So this is going to be cos theta. So you got Shin theta. So what is this formula? Shin of 2 theta. Very important. Shin of 2 theta is equal to 2 times of cos theta Shin theta, or 2 times of Shin theta cos theta. So whatever you want, you can write it. So all important, one more thing is the equivalent for cos theta. So cos theta is e raised to the power theta. It's not negative here, so it should be positive here. So positive e raised to the power negative theta divided by 2. So these are some of the important results that are necessary in handling not this problem but many questions, relevant questions. So having mentioned this, what we are going to do is we will add to go back to the question. Of course, in the place of theta, okay, we have to substitute at. So this is going to be e raised to the power of at negative e raised to the power of negative at divided by 2. This is what we've got. Now we will have to place this quantity inside the Laplace operator. So that's going to be Laplace transform of this. So this can be rewritten. I can take this half out. Now I'm going to write this as Laplace transform of e raised to the power at followed by Laplace transform of e raised to the power negative at. Okay, if you are very much bothered about the parenthesis, you can change it to flower parenthesis. But it doesn't matter, as I mentioned to you, it's by convention people use it. Flower or square, the operator is Laplace. So now we will have to use Laplace transform. So let me write down to the formula. So we know that the Laplace transform of e raised to the power at is going to be equal to 1 over s negative a. We know this, right? So we can substitute that. But what happens, we have already shown this result also. What happens if you get e raised to the power negative at? So what would be the case in that case? So in place of a, I get a negative a. So this is going to be 1 over s positive a. That's the outcome for this. So using these, so if I were to take this as 2, so using these into, we get, so what do we get when we use this? This is going to be 1 over 2 times, in place of this is going to be 1 over s negative a, there's a negative sign followed by 1 over s positive a. Now you can simplify this. So the denominator is s negative a times s positive a. This is going to be s positive a negative of s negative a, which is equal to 1 over 2 times of positive s negative s gets cancelled. A added with positive a will give you 2a divided by a s negative a times s positive a will give you s squared negative a squared. the 2 can be cancelled, giving you a over s squared negative a squared. So we got an important result. What is that? Laplace transform of Shin at is equal to a over s squared negative a squared. So this would mean the Laplace transform of Shin 60, okay, is equal to 6 divided by s squared negative 36. So that's the solution for this question. Students, now we are expected to compute Laplace transform of cos of 90. So as I mentioned to you, it would be much better if I first showed you how to obtain cos of 80. Now for this we would have to go and review the formula of cos theta. Now cos theta is e raised to the power of theta followed by a positive sign and then e raised to the power of negative theta divided by 2. So therefore, if I were to write cos of 80, this is going to be e raised to the power of 80, positive e raised to the power negative 80 divided by 2. So I will be using this representation over here. So let me box this off. So this is equal to Laplace transform of e raised to the power of 80, positive e raised to the power negative 80 divided by 2. Now, but we know that the Laplace transform of e raised to the power of 80 is equal to 1 over s negative a. And this would mean Laplace transform of e raised to the power negative 80 is going to be 1 over s positive a. So if I were to take this as 2, using these, 2 can now be rewritten as, I'm going to take the half out and rewrite this as Laplace transform of e raised to the power 80 positive Laplace transform of e raised to the power negative 80. So this is equal to 1 over 2 of Laplace transform of e raised to the power 80 is going to be 1 over s negative a followed by 1 over s positive a. If I were to take the LCM, I would have s negative a times s positive a, and this would be s positive a positive s negative a. Negative a positive a gets cancelled, giving me 2 times of s divided by s negative a times s positive a would give me s squared negative a squared times 2. The 2 can be cancelled, giving me s over s squared negative a squared. So this is the Laplace transform of cos 80. But the question wants us to compute cos 90. So therefore Laplace transform of cos 90 is equal to s over s squared negative 9 squared, which is s over s squared negative 81. So this is the solution for the question. Students, we've been given this problem. We are expected to find the Laplace transform of u of t negative a. Now what is this? This is called as the unit step function. So before we could continue to solve the solution or solve the problem, we would have to know what the unit step function is. So let me define that for you. So unit step function is defined as follows. Now it's always represented as u of t. Now u of t is equal to 0 if t is less than 0. Now what is t? T is actually time. And it is equal to 1 if t is greater than 0. So if time is negative, u of t is 0. If time is positive, u of t is 1. So that is the most important definition that you will have to know. So having obtained this, let us move on. Now what I wish to do now next is to draw the step function, how exactly the step function will look. So a brief description or a brief diagram would be this. So for all values of t which is less than 0, say for example I'm having negative 2 here and positive 2 here, and this is say 1, positive 1. Now for all values of t that is going lesser than 0, so the diagram would be over here, the line would be over here. For values which are greater than 0, the line would be like this. So this is the straight line, step function, straight line, it goes like this. And in this case, since I already have the axis, that's the reason I have shaded it. So actually speaking, you need to draw the line. So this is how the step function looks like. Okay, so having given this, now there is some other important information also you will have to know. At t is equal to 0, say for example I have given the value to be strictly greater than 0 and less than 0. Now what if t is equal to 0? So in that case you will have to have a circle here, a small hole here. Of course we don't want to go into the concept of discontinuity here. So just for the sake of this question I would leave the definition to be like this. So to keep it brief, this definition is sufficient enough. Now the point here is we have been given u of t negative a. Okay, so this is the important point, that a. So if I were to represent that a, say for example instead of a, if I were to have some value, say a being equal to 3, then I'm talking about a unit function, unit step function of the form u of t negative 3. So if I were to draw this graph for this, then the graph would be something of this fashion. So it would start off from 0, and this 3 would be my benchmark or bench point, and we were interested in values of t which is less than 3 and values of t which is greater than 3. So this is what we are looking forward to. So for values of t less than 3, this would be the graph, and immediately it would rise for values of t. If I were to take this as 1, for values of t greater than 3, then the graph would rise up, right? Because by definition this would be the graph that we would get for values of t greater than 3. So having mentioned this, let us go on to solve the question that we've been given. So this is the required question. So this is what we need to do. We need to find the Laplace transform of the unit step function of t negative a. So we are talking about t less than a and t greater than a. Now the limit. So let me just write that down. So Laplace transform of u of t negative a is equal to, from the definition of Laplace transform, this is going to be 0 to infinity e raised to the power negative st times u of t negative a, right, times dt. But we are only interested for that range or those values of t greater than 3, because less than, in fact when you're talking about values of t less than 3, it's actually over here. So there is no point in considering that interval. So I'm going to reform the integral from the definition of step function as, instead of saying 0 to infinity, I would be starting from a to infinity. So e raised to the power of negative st. Of course this will be 1, so I need to just place here dt. So that's fair enough. So now we got something to work with. So this is equal to, if I were to integrate this, this is going to be e raised to the power of negative st divided by the coefficient of t is s. So let me place that negative s. The limits are from a to infinity. So I can rewrite this as 1 over s with a negative sign, and you got e raised to the power negative st, and the limits are a to infinity. Now applying the limits, we get, so if we were to apply limits, this would be equal to negative 1 over s e raised to the power of negative s times infinity followed by negative sign e raised to the power negative s times, and the limit is going to be a there, right, upper limit minus lower limit. Now clearly s is greater than, in fact s is a greater value, right? If we were to talk about the value of s, we know that s is greater than a greater than 0 when we were dealing with a, but we are not dealing with a now. We are actually dealing with s as a quantity, so s is clearly greater than 0. Now since s is greater than 0, this quantity is going to be smaller, so that means this quantity will vanish. So this is going to give me negative 1 over s of negative e raised to the power negative s times a. Negative, negative, positive, so this is going to be e raised to the power of negative s times a divided by an s with the condition that s is greater than 0. So this is your solution. The most important point when students see a step function, there would be an element of confusion how to move forward. So that confusion would be annihilated or removed by this all important definition of step function, and then extending a bit further, what if the value of a be some 3, and understanding this concept. So that these two concepts together would help us to reduce this integral to this, and subsequently you will be in a better position to solve this question. So this is the first part of the concept of Laplace transforms. So I will stop here for this class and I will continue again in our next class. Thank you students, enjoy your day. Students, we are expected to find the Laplace transform of f of t negative a times u of t negative a. Now this is a unit step function and we've got a function involving t minus a. So what I'm going to do is I'm going to state the definition. From definition of Laplace transforms, L of f of t is equal to integral 0 to infinity e raised to the power negative st times f of t times dt. So we know this clearly. So using this definition, I can rewrite this Laplace transform of f of t negative a times u of t negative a to be as integral 0 to infinity e raised to the power negative st f of t negative a times u of t negative a times dt. Now u of t negative a is a unit step function, and because of this fact, and since the shift is a units, I can rewrite this as a to infinity e raised to the power negative st f of t negative a times dt. Now I need to integrate this. So for that I need to take t negative a to be as some p. If I were to move this a onto the other side, I would have t is equal to p positive a. If I were to differentiate, I get dt is equal to dp. Now let me substitute. This is equal to, I'm not touching the limits as yet, e raised to the power negative s of, in place of t I substitute p positive a times f of t negative a is p and my dt is dp. Now let us handle the limits. Now when t is equal to a, I get a negative a is equal to p. This means p is equal to 0. So place the 0. Now when t is equal to infinity, I get infinity negative a is equal to p. This means p is equal to infinity. So substitute there. So this is what I've got. Now I can rewrite this as integral 0 to infinity e raised to the power negative s times p times e raised to the power negative s times a times f of p times dp. Now this is a constant, so take that out. E raised to the power negative s times a integral 0 to infinity e raised to the power negative s times p times f of p times dp. Now from definition of Laplace transform, what exactly do we have? We got L of f of t is equal to integral 0 to infinity e raised to the power negative st times f of t dt. In place of t, I've got a p, a p, a p. So this is actually the definition of Laplace transforms. But what is this? This is nothing but capital F of s. So I can rewrite this to be as e raised to the power negative s times a times f of s. So this is my Laplace transforms of f of t negative a times u of t negative a. So that is the solution for this question. Students, this is example number 15. In this question, we are expected to find the Laplace transform of f of t times u of t negative a, which is a unit step function. Now, we already have a result. We know that Laplace transform of f of t negative a times u of t negative a is equal to e raised to the power of negative sa times f of s. We know this, but in this case we are being given f of t. So what I wish to do is I wish to let h of say t negative a be equal to some f of t. So hence, if I were to take this as 1, we can rewrite 1 as Laplace transform of, in place of f of t, I would be substituting h of t negative a times u of t negative a, the unit step function. So using the result, we can rewrite this to be as e raised to the power of negative sa times f of s. F of s is nothing but Laplace transform of f of t. In this case, it is going to be the Laplace transform of h of t. We have to have f of t in the final result, but we are having h of t. So we started with h of t negative a to be equal to f of t. Now just consider here, we don't want t negative a. In fact, in place of t negative a, we need to have h of t. So if I were to replace t negative a as t, then naturally this t would become f of t positive a, and this would be h of t. You follow me? Because t negative a should be t, this has to become t, and t should, if I were to take t negative a as t, then naturally t positive a would take the place of t because of the shift. So h of t will now be equal to f of t positive a. So I can rewrite this result. These are all not required, just for sake of understanding. So this is equal to e raised to the power negative sa Laplace transform of, in place of h of t, we substitute f of t positive a. So that is the final result for this question. Students, we are given this question. We are expected to find the Laplace transform of t negative 3 raised to the power of 3 times the unit step function of t negative 3. The shift is 3 units. Now for this I would be using the following result. We know that the Laplace transform of f of t negative a times u of t negative a is equal to e raised to the power of negative sa times f of s. Now from this result I can rewrite this to be as e raised to the power of negative, in place of a I would be substituting 3. Actually it talks about this shift 3, and then that has to be multiplied with f of s. So in this case it has to be the Laplace transform. Now we got t negative 3 raised to the power of 3, right? The shift is 3 units, so you ignore the shift and just place t there. So that's going to be Laplace transform of t cubed. Now we know that Laplace transform of t to the power of n is equal to n factorial divided by s raised to the power of n positive 1. So this would mean this is equal to e raised to the power of negative s times 3. I can rewrite it as 3 times s times Laplace transform of t cubed is n factorial. That's going to be 3 factorial divided by s raised to the power of 3 positive 1, which is equal to 3 factorial is 6. So I can rewrite this as 6 times e raised to the power of negative 3s divided by 3 positive 1 is 4. So this is the solution for this question.
Now, just in case, we got plenty of 3's here. We have a 3 here, we got a 3 here, we got a 3 here. So, I would like to show you one more illustration. Say, example 17. So, you got a Laplace transform of, say, t negative, say, 12 raised to the power of 4 times unit step function of t negative 12. So, this is a shift of 12 units. So we expected to find this question. So using this, I can rewrite this as e raised to the power, the shift that counts. So it's going to be negative s times of 12 times Laplace transform of t raised to the power of 4. Okay, this 4. And using this formula, this is e raised to the power negative 12 times s. N factorial is 4 factorial divided by and s raised to the power of 4 positive 1. So this is going to be 4 factorial. You can find out 4 times 3 times 2. 4 3s are 12. 12 times 2 is 24. So that's going to be 24 times e raised to the power negative 12 times s divided by s raised to the power 4 positive 1 will give you s raised to the power of 5. Now I did this question just to have a differentiation between the quantities that we see for the shift and for the power that is present as an index. So we will move on to the next question, students. Students, we are given this question. This is, I think it's example number 17. We are expected to find the Laplace transform of t cubed times unit step function of t negative 2. Now we would have to use the result. We know that the Laplace transform of f of t times u of t negative a is equal to e raised to the power negative sa times the Laplace transform of f of t positive a. So in place of t, we have to substitute the shift t positive a. So that is very critical. So what we are going to do is we are going to rewrite this as the shift is 2 units, so it's going to be e raised to the power negative s times 2 times Laplace transform of the shift 2 units has to be substituted as t positive 2 inside the component t raised to the power 3. So that would mean I would have to find the Laplace transform of t positive 2 raised to the power 3. So that is what is required here. So rewriting this is going to be e raised to the power negative 2 times s times, I need to find out the Laplace transform of, now I need to use a positive b whole cubed. So if I want to expand this, a positive b whole cube, I get a cubed positive b cubed positive 3 times a squared b positive 3ab squared. This is what is needed. So this is going to become t cubed positive 2 cubed positive 3 times t squared times 2 positive 3 times t times 2 squared. This is rewritten as e raised to the power negative 2 times s times Laplace transform of t cubed. 2 cubed is 8. This is 3 times 2 is 6 times t squared. 2 squared is 4. 4 times 3 is 12 t. Now this is nothing but e raised to the power negative 2s of, let me have this flower parenthesis, I'm going to take the operator inside, Laplace transform of t cubed plus 6 times Laplace transform of t squared plus 12 times Laplace transform of t plus, I got no other option but to write 8. In fact, I can write this as 8 times t raised to the power 0. Fair enough, right? Now we know that the Laplace transform of t power n is equal to n factorial divided by s raised to the power of n positive 1. So Laplace transform of t cubed, what is that? That is going to be 3 factorial divided by s raised to the power 3 positive 1. 3 factorial is 6. This is s raised to the power 4. Okay, now having got that, let us find out what is Laplace transform of t squared. What is that? That's 2 factorial divided by s raised to the power 2 positive 1. 2 factorial is 2, s raised to the power 3. and Laplace transform of t is going to be 1 factorial divided by s raised to the power 1 positive 1, which is nothing but 1 over s squared. So we got all of this. And Laplace transform of t power 0 is 0 factorial divided by s raised to the power 0 positive 1, which is nothing but 1 over s. So substituting that, this is going to be e raised to the power negative 2 times s. T cubed, Laplace transform of t cubed is 6 over s raised to the power 4 positive. 6 times Laplace transform of t squared is 2 times over s cubed positive. 12 times Laplace transform of t is 1 over s squared plus 8 times Laplace transform of t0 is 1 over s. So it's going to be 1 over s. So if I were to rewrite this, it's going to be e raised to the power negative 2 times s. I can rewrite this as 6 over s to the power 4 positive 12 over s cubed positive, this is 12 over s squared positive 8 over s. So that is the solution for this question. Students, we are given this question to find the Laplace transform of delta of t negative a. Now this delta is actually what is called as the delta function. In fact, we call it as the direct delta function. Now before we could proceed on with obtaining the solution for this question, it becomes imperative that we understand what the delta function is. Now the delta function is defined to be as delta of x to be equal to 0 for values of x which is actually not equal to 0. So the delta function takes the value 0 for all values of x which is not equal to 0, and it takes the value infinity for x is equal to 0. So this is a very important and pertinent definition for delta of x. So let me reiterate one more time. Delta of x takes the value 0 for all values of x not equal to 0, and it takes the value infinity when x is equal to 0. So at x is equal to 0, the function heads to infinity. Now if you were to integrate this from minus infinity to positive infinity, delta of x times dx, then it would have a unit area with the singularity being crossed at 0. So this is also a very important understanding. So now the all important question is, how do we get the delta function? Well, I can give you a simple example using step up and step down function. So let me just have this illustration. So I'm going to have this x and y axis. Now we are looking at a function which is going to be just existing around the origin, and it is going to be 0 elsewhere. Now let me just take a small value, say epsilon over on the left side, negative epsilon, and positive epsilon on the right side. Now we got a function exactly at negative epsilon. The function steps up and reaches a certain value, and then it steps down. Now the width of this function is going to be 2 epsilon, and in order for the area to be equal to 1, the value attained here, the height attained here, should be 1 over 2 epsilon. So from this step up and step down function, I am going to obtain the delta function. So the question now comes is, how do I represent this by means of a function? So I'm going to write this as delta suffix epsilon of x. Now clearly, if you were to see the graph at negative epsilon, the function steps up. So I'm going to have u with the suffix negative epsilon of x, and at epsilon it steps down. So this is going to be u suffix epsilon of x. So this is going to be a representation for this step up and step down function. Now from here, if I want to write the delta function, the delta function can be written as delta of x is equal to limit epsilon tending to 0 of delta epsilon of x. So this is how we get the delta function. Let me show you one important property or characteristics of our delta function. Now if we were to have an integration minus infinity to infinity, say f of x with the delta function delta of x negative a and with the differential operator dx, then clearly we know that delta of x minus a would become 0 when x minus a is equal to 0. So having known that particular fact, the delta function becomes 0 when x minus a becomes equal to 0. That would mean it doesn't matter what the value that the function f of x takes. So I can rewrite this as integral minus infinity to infinity f of a times delta of x negative a times dx. Now we got f of a and we can take that f of a out. So that's exactly what I'm going to do. So let me just place f of a here, followed by integral negative infinity to infinity delta of x minus a times dx. Now clearly we know from the definition the area for this is equal to 1. So that would mean that we got this to be equal to f of a. So this is a very important property that would be used in the field of engineering. Students, let us now work out the question. We are expected to find the Laplace transform of delta of t negative a. Now from the definition I already mentioned, delta of t negative a can be defined in the following manner, that the function takes the value 0 if t is not equal to a, and it takes the value infinity when t is equal to a. So having defined this, because this follows from the original definition of delta function. So now from the definition of Laplace, we can rewrite this to be as integral 0 to infinity e raised to the power of negative st followed by delta of t negative a times dt. Now we are very much bothered that for t minus a equal to 0, this becomes equal to 0. So we don't want that. In other words, it doesn't matter what this value takes when t minus a is not equal to 0. Because if t minus a is equal to 0, this delta function becomes equal to 0, and that is when we get the issue. So having stated that, I can rewrite this as integral 0 to infinity e raised to the power of negative s times a times delta of t negative a times dt. Now this can be further rewritten as e raised to the power negative s times a integral 0 to infinity delta of t negative a times dt. Now we know this area, that's going to be equal to 1, so this would mean e raised to the power negative s times a of 1, which is equal to e raised to the power negative s times a. So this is the solution. So though the integral appears to be complex, yet the solution is easily achieved from the definition of delta function. Welcome students. Today we will start off by doing this question, Laplace transform of f of at. Now by definition we know that Laplace transform of f of t is equal to integral 0 to infinity e raised to the power of negative st f of t times dt, and we write that to be equal to f of s. In other words, you can also state that f of s is equal to integral 0 to infinity e raised to the power negative st times f of t times dt. Now with this definition we will be working out with this. So let us just consider Laplace transform of f of at. Now in place of t we have got at, so this is equal to integral
0 to infinity. In place of the function, we will just have to use at, because in place of t we have got at. So this is going to be e raised to the power negative st times the function is at times dt. And don't write anything for f of s. So let us just focus on this particular transform. Now what I wish to do is I would have to change this at to represent a single function. And more so, another important fact you got to know here is the value of a is greater than 0. It's not negative. Now what I would do is I would just take, let sum p be equal to at, and I differentiate this. So dp will be equal to a times dt, and from here I can write dt to be equal to dp over a. Okay, so this is going to be equal to, I'm not going to change the integration limits for now. Let me just make the substitutions. Now this is e raised to the power negative s. In place of t, from here t is equal to p over a. Right, so substitute p over a times f of, in place of at I've got p, in place of dt I've got dp over a. Now what happens to the limits? Let us handle the limits here. When t is equal to 0, the limits of p will be equal to 0. When t is equal to infinity, p will be equal to infinity. So this is going to be 0 to infinity. Now a is a constant, so you take that out, so it's going to be 1 over a. Integration is from 0 to infinity, e raised to the power of negative s p over a f of p times dp. So this is what we have got. Now clearly, if you were to compare here with the original definition, I've got a p here instead of t, I've got a p here instead of t, but the only situation that I've got here is I've got a negative s times p over a. I got to have a t. In other words, I got to have a p alone here. So what I'm going to do is I'm going to rewrite this as 1 over a integral 0 to infinity e raised to the power. Instead of a occurring below p, I would like to write this as negative s over a times p times f of p times dp. So this is the way I would like to write. Now if you were to see this, in place of s I've got s over a. Okay, so let me write this like this: 1 over a integral 0 to infinity e raised to the power negative of s over a times p times f of p times dp. So now you can see that in place of s I've got s over a. Of course the negative sign is occurring in both the terms, and I've got a constant 1 over a. Now this is just going to be following us, but if you were to see the integration, this is similar to the integration definition that we add for Laplace transform of the function f of t. So I can clearly write, in place of f of s, I should say in place of s, I can substitute s over a. So that would mean I now have f of s over a. I hope you are following this. When I have s, I got the function to be as s. When I have s over a, I need to have the function as s over a, f of s over a. So therefore, to sum up Laplace transform of f of at is equal to 1 over a f of s over a. So students, we are going to find out how exactly we could use this result. Students, we will be using this definition to solve a few questions. So foremost, let us find out the Laplace transform of Shin at. Now we already know that the Laplace transform of Shin t is equal to 1 over s squared negative 1. Now by using this definition, Laplace transform of Shin at can be rewritten as 1 over a f of s divided by a. So that would mean, in place of, say this, let me rewrite this to be as f of s being equal to 1 over s squared negative 1. So in place of s, all I need to do is substitute s over a. So this would mean I get 1 over a, 1 over s over a raised to the power 2 negative 1. Now I can rewrite this as 1 over a of 1 divided by s squared over a squared negative 1, which can be rewritten as 1 over a of 1 over, I'm taking a squared as the LCM, so it's going to be a squared negative a squared divided by a squared. If I were to flip this, I would get 1 over a. This is going to be a squared over a squared negative a squared. So clearly a and a can be cancelled, giving me a over a squared negative a squared. This is my Laplace transform of Shin at. Now if someone were to ask us, how are we to show that this is true? So it can be easily shown. So let us just consider, I'm going to show you that Laplace transform of Shin at is truly a over s squared negative a squared. Now we know that Shin t can be rewritten as, in fact, Shin theta, or let me use Shin theta. Shin theta can be written as e raised to the power of theta negative e raised to the power negative theta divided by 2. Okay, this is the expansion for Shin theta. So Shin at can be rewritten as e raised to the power of, in place of theta, substitute at. So it's going to be at negative e raised to the power of at divided by 2. Now this can be rewritten as, I want to take 1 over 2 out. In fact, this can be Laplace transform of e raised to the power of at negative e raised to the power of negative at, which can be rewritten as 1 over 2 Laplace transform of e raised to the power of at negative Laplace transform of e raised to the power negative at. Now this is equal to 1 over 2 times. Now Laplace transform of e raised to the power at, what is that? That is nothing but 1 over s negative a. Negative, what is the Laplace transform of e raised to the power negative at? That is going to be 1 over s positive a. Now if I were to take the LCM s negative a times s positive a, I would have s positive a negative of s negative a. So that is going to be equal to 1 over 2 times s positive a, let me rewrite it like this, positive a negative of s positive a divided by s squared negative a squared. Now positive s negative s gets cancelled, so s add a added with a will give me 2a divided by s squared negative a squared. So 2 can be cancelled, giving me a over a squared negative a squared. So what is this? This is Laplace transform of Shin at. So this is exactly what we have got using the formula. Okay, one more illustration in terms of cosine. So imagine you are asked to find Laplace transform of cos at. I'm going to use this definition, Laplace transform of f of at is equal to 1 over a f of s over a. And by this definition, I'm going to apply this definition to Laplace transform of cos t, which is equal to s divided by s squared positive 1. So therefore Laplace transform of cos at is equal to 1 over a f of s over a. This is actually f of s, right? So this can be rewritten as 1 over a. In place of s, I need to substitute s over a. So it's going to be s over a divided by s over a raised to the power 2 positive 1. So I can rewrite this as 1 over a of s over a divided by s squared divided by a squared positive 1 is equal to 1 over a s over a. LCM is a squared, so it's going to be s squared positive a squared divided by a squared. I can rewrite this as 1 over a. Now I can place a s, move the a to the denominator. In fact, let me just have it like this, and then I will use this step to rewrite this as s squared positive a squared. If I were to flip it, this will be going up to the numerator. So this 1, I'm going to rewrite it as a squared. So this is going to be equal to, a can be cancelled, giving me a. Now s slash a, this can be rewritten as s with a being pushed to the denominator, and then you got s squared positive a squared. So a can be cancelled, giving me s over s squared positive a squared. So this is nothing but the Laplace transform of cos at. Students, we are expected to find the Laplace transform of e raised to the power at times f of t. Now we know that, say, Laplace transform of f of t to be equal to integral 0 to infinity e raised to the power negative st times f of t dt, which is equal to f of s. So we know this as a definition. Now I will be using this definition for this quantity. Now this entire thing is taken as a function. So if I were to do that, then I can rewrite this to be as integral 0 to infinity e raised to the power negative st times, in place of f of t I would be placing e raised to the power at times f of t times dt. Now this can be rewritten as integral 0 to infinity. I would be taking t out, so this is going to be negative s positive a times t times f of t times dt. Now just observe here, I've got a negative sign before s. So what I would do is I would take the negative sign out. So this is going to be integral 0 to infinity e raised to the power negative of s. So when I take the negative sign out, I would get negative a here, because negative times s would give me negative s, negative times negative a would give me positive a times t times f of t dt. Now just watch this. This is nothing but negative of s negative a. This is nothing but negative s. And what do we get? F of s. So this should be equal to f of s negative a. So clearly a is the shift, and this f of s negative a would give us the Laplace transform for e raised to the power at times f of t. Now let me give you an illustration. Okay, let me use this space here. Imagine you are asked to find the Laplace transform of, say, t raised to the power of 5 times e raised to the power of, say, some 3t. Right? Now when you see this question looks really difficult, but it is not so. Now what I wish to do is I would like to write this as Laplace transform of e raised to the power 3t times t raised to the power 5. Now the shift is 3 units. So according to this, first what I would do is I would just find out, or I will say we know that Laplace transform of t power n is equal to n factorial divided by s raised to the power n positive 1. So therefore Laplace transform of t raised to the power of 5 is equal to 5 factorial divided by s raised to the power 5 positive 1. That's going to be 6. Right? So from here, hence I can conclude Laplace transform of e raised to the power 3t times t raised to the power 5 is equal to, there is no change in this 5 factorial, but in place of s I would have to substitute s negative 3,
and that has to be raised to the power of 6. So this is the final answer to the question. Of course, 5 factorial is equal to 120. Probably you can write that down and then divide by s negative 3 raised to the power of 6. So that is the solution for this question, students.
Students, we've been given this question. We expected to find the Laplace transform of e raised to the power 3t times cos 2t. Foremost, let us know what is the Laplace transform of cos at. It's nothing but s over s squared positive a squared. Now, having known this, we will also use the Laplace transform of e raised to the power at times f of t. What is this equal to? This is nothing but f of s negative a. So, if I were to take this to be as f of s, capital F of s, then this would mean Laplace transform of, first let me write the Laplace transform for cos 2t. Now Laplace transform for cos 2t is equal to s divided by s squared positive 2 squared, which is equal to s over s squared positive 4. Now we are expected to find the Laplace transform for e raised to the power of 3t times cos 2t. So using 1, we get the Laplace transform of e raised to the power 3t times cos 2t to be equal to f of s negative 3, because in place of a we got 3, so let me write that down. So this is going to be rewritten as, in place of s, I would have to substitute s negative 3. So that's going to be s negative 3 divided by s negative 3 raised to the power 2 positive 4. So this is going to be s negative 3 divided by, expand this, s squared negative 6 times s positive 9 positive 4, which is equal to s negative 3 divided by s squared negative 6s, 9 added with 4 will give me 13. So this is going to be my Laplace transform of e raised to the power 3t times cos 2t. Students, in this question we are expected to find the Laplace transform of t times f of t. Now to do this question, first let us write down the definition of Laplace transform. We know that f of s is equal to integral 0 to infinity e raised to the power of negative s times t times f of t times dt. This is the definition. Now we need to produce a t there. Now if we are given y is equal to e raised to the power of 2x, if you want to find dy over dx, this is going to be e raised to the power of 2x times differentiation of this quantity 2x. Now if I were to be given, say, y is equal to e raised to the power of negative 2x, then dy over dx is going to be differentiation of this e raised to the power of negative 2x, then differentiation of this, that's going to be negative 2, which is actually the coefficient of x. So with that being said, let me just operate the left and the right with du over ds. So this is going to be du over ds of capital F of s is equal to d over ds of integral 0 to infinity e raised to the power of negative s times t times f of t times dt. Now why am I differentiating this? Because I want to have a t there. If I were to differentiate it with reference to t, I wouldn't be able to get the t. That is the simplest fact. Now this is actually Leadness Rule. Okay, Leadness Rule, which is actually a powerful rule because it combines differentiation with integration. So have that in mind. Now I would like to bring this d over ds operator inside. Now have this important concept in mind. Now inside the integral we got actually t to be the important variable. T is controlling this region, but we are differentiating with reference to s. So that means we will have to only perform the differentiation partially. So this is going to be dou over dou s of e raised to the power negative s times t times f of t times total differential dt with the limits being 0 to infinity. The reason being the integrand consists of two variables, t and s. Apparently t is the functional variable. That is the reason when I bring this total differentiation inside the integral, it changes into partial differentiation. Now I will be differentiating e raised to the power of negative st partially with reference to s. So that would mean I now have integral 0 to infinity. When I differentiate the quantity e raised to the power of negative st, I get e raised to the power of negative st. The coefficient of s with reference to, or I should say the coefficient of s is negative t. So thus place negative t there because it follows from the differentiation. The coefficient of x here is negative 2, so I multiply by negative 2. So the coefficient of s here is negative t, so I multiply it by negative t. Followed by f of t times dt. Rewriting, I would now have d over ds of capital F of s to be equal to integral 0 to infinity. Now I would like to place the negative sign out and write this as t times of e raised to the power of negative s times t times f of t times dt. So this is what I've got. Now I can push this negative sign to the left. So that would mean I can rewrite this quantity as integral 0 to infinity t times e raised to the power negative st times f of t times dt is equal to negative d over ds of f of s. So this is a very important result. I will be showing you how exactly to use this result. Okay, now how are we going to do this particular question? Integral 0 to infinity t times cos at times dt. Now this is very much similar to integral 0 to infinity t times f of t times dt, where the right hand side is equal to d over ds of f of s. We know this result. So clearly, if I were to take this as 1, from 1 we observe that f of t is equal to cos at. So Laplace transform of f of t is equal to Laplace transform of cos at, which is equal to s divided by s squared positive a squared. This is the Laplace transform. So this would mean integral 0 to infinity of t times cos at times dt is equal to negative d over ds of f of s, which is equal to d over ds of, I need to differentiate s over s squared positive a squared. So this is equal to, now differentiation of u over v is equal to v times u dash minus u times v dash divided by v squared. So this is equal to negative s squared positive a squared raised to the power 2. Now v is s squared positive a squared. Differentiation of s is going to give me 1, followed by negative s times differentiation of s squared positive a squared, that's going to be 2 times of s. So this is rewritten as negative s squared positive a squared negative 2 times s squared divided by s squared positive a squared raised to the power of 2. Now this is equal to s squared added with negative 2 times s squared will give me negative s squared positive a squared. There is a negative sign divided by s squared positive a squared raised to the power of 2. If I were to take the negative sign out, so this is going to be if I were to bring the negative sign inside, this is going to give me positive a squared negative a squared divided by s squared positive a squared raised to the power of 2. So therefore, what is the conclusion? Integral 0 to infinity t times cos at dt is equal to s squared negative a squared divided by s squared positive a squared raised to the power of 2.
So this is the final answer to this question. Now this is a special case. What if I have the degree of t to be any n? In that case, we would have the result to be as -1 raised to the power of n times d over ds of capital F of s. So, and more so, the differentiation, the number of times we need to differentiate would be n. So this is a very important formula that we have to employ, or I would say have it in mind. Now let me just go and do a question. Say, for example, if I have, say, if we are given to find the Laplace transform of t raised to the power of 4 times, say, some e raised to the power of 3t. So what we would do, of course, we can also use the alternative methods for this, but I would like to use the method that we have studied. So to start off with, I would just say that this is similar to Laplace transform of t raised to the power n f of t, which is equal to -1 raised to the power n differentiation d over ds, with the degree being n, of f of s, where my t power n here is t power 4 and my f of t is equal to e raised to the power of 3t. So this would mean Laplace transform of t power 4 e to the power 3t is equal to -1 raised to the power of 4 times differentiating this 4 times of f of s. Okay, now also we know that the Laplace transform of e to the power at is equal to 1 over s negative a. This means Laplace transform of e power 3t is equal to 1 over s negative 3. So hence Laplace transform of t power 4 e to the power of 3t can now be rewritten as -1 raised to the power 4 is +1. I need to differentiate this 4 times, 1 over s negative 3. So let me show you that differentiation. So I'm going to use u over v formula. So u over v, if I were to use this, is going to be v times u dash minus u times v dash over v squared. So the first time is going to be s negative 3 raised to the power of 2, and it's going to be s negative 3, v is s negative 3. Differentiation of 1 is going to be 0, followed by 1 times differentiation of my v is 1. So that's going to give me -1 divided by s negative 3 raised to the power of 2. First differentiation. Second differentiation. So let me have first differentiation. The second differentiation, this is going to be u over v. So it's going to be s negative 3 raised to the power of 2 times differentiation of 1, 0, followed by negative of -1 times differentiation of this is going to be 2 times of s negative 3, right, times differentiation of s is going to be 1. This is divided by s negative 3 raised to the power of, this is already 2, so this is going to be 4. So this is going to be +1, 2 times of s negative 3 divided by s negative 3 raised to the power of 4, which is going to be 2 over s negative 3 raised to the power of 3. This is my second differentiation. Now let me just perform my third differentiation. Third differentiation is going to be s negative 3 raised to the power 3. Differentiation of 2 is 0, followed by -2 times differentiation of s negative 3 raised to the power of 3 is going to be 3 times of s negative 3 raised to the power of 2 times the differentiation of s divided by s negative 3 raised to the power of 3 the whole square. That's going to be s negative 3 raised to the power of 6. So this will go away. This is going to be -2 times 3 is 6 times s negative 3 raised to the power 2 divided by s negative 3 raised to the power of 6. This is going to be -6 over s negative 3 raised to the power of 4. So this is my third differentiation. Now I want to squeeze the fourth differentiation over here. So this is my fourth differentiation. So This is s negative 3 raised to the power of 4. Differentiating constant is giving me 0. Negative of negative 6 times. Differentiation of this is going to be 4 times of s negative 3 raised to the power of 3 times differentiation of s is 1 divided by s negative 3 raised to the power of 8. So this is going to give me positive 24 times s negative 3 raised to the power of 3 divided by s negative 3 raised to the power of 8, which can be rewritten as 24 times s negative 3 raised to the power of 3 will get cancelled out, giving me s negative 3 raised to the power of 5. So the outcome for this is going to be 24 over s negative 3 raised to the power of 5. So this is my Laplace transform of t power 4 e raised to the power 3t. Alternative method to differentiate the quantity d4 ds4. The function given is actually 1 over. So let me write the step preceding this. So this is going to be differentiating this 4 times of 1 over s negative 3. This is what we have got. Now what I wish to do is I would like to move this to the numerator. If I were to do this, I will get s negative 3 raised to the power of negative 1. Right? So I will be differentiating it for the first time. So that would give me d cubed ds cubed of, see, this is like 1 over x squared. When you take it to the numerator, this becomes x to the power negative 2. Now if you want to differentiate this, if you want to differentiate say d of x to the power negative 2, it's nothing but negative 2 times x power negative 2 negative 1, which is negative 2 times x to the power negative 3, right? This is the way we have to follow, or I should say apply this. So when you differentiate this, this is going to be negative 1 times of s negative 3 raised to the power of negative 1 negative 1. Right? I hope you can see that. I can rewrite this as d cubed over ds cubed of, this is negative 1 times s negative 3 raised to the power of negative 1 gives me negative 2. Now after this we need to differentiate it one more time. So this is going to give me d squared over ds squared of negative 1 times negative 2 times s negative 3 raised to the power of negative 2 negative 1. Of course the differentiation of s is going to be 1. You don't have to write it, but just for the sake of consistency I'm showing you. So this can be rewritten as d squared of ds squared, negative 1 times negative 2 gives me positive 2 times s negative 3 raised to the power of negative 3. Now I'm going to differentiate it one more time. So that is going to give me d over ds of negative 3 times 2. That's going to be written in this fashion, s negative 3 raised to the power of negative 3 negative 1. That's going to be d over ds of 2 times 3 is going to give me negative 6 because of the negative sign. So it's going to be s negative 3 raised to the power of negative 3 negative 1 gives me negative 4. Now this I need to do one more differentiation. So that would mean negative 6 multiplied with negative 4 times s negative 3 raised to the power of negative 4 negative 1. 6 times 4, 24, positive 24 because of the negative sign. So that has to be multiplied with s negative 3 raised to the power of 5, which is rewritten as 24 over s negative 3 raised to the power of 5. So this is my solution. This is exactly what we got when we adopted the long division, or I should say the long way of quotient differentiation. Students, in this question we are expected to find the Laplace transform of f of t over t, and we will have to obtain the result. Now if I were to take this as f of t, then I can rewrite this as integral 0 to infinity e raised to the power of negative st times f of t over t times dt. So we are actually trying to obtain the result for this. Now you can clearly see that in the previous question we had the t in the numerator. Now in this question we got t in the denominator. So that means for the previous question we used the technique of differentiation. For this question we will use the technique of integration. So for that, let me just show you this. Consider, say, e raised to the power of negative p times t times dp. Now if you were to integrate this is going to give me e raised to the power of negative p t. P is the variable, right? So you have to divide this entire thing by the coefficient of p. So the coefficient of p in this case is negative t. So this is going to be negative t here. And I need to, if I don't place the limits, I will have to use the arbitrary constant. But I don't want the arbitrary constant. I want to have limits because I want to eliminate the arbitrary constant. So this is what I have got. Now, if I were to place a lower limit, say for example 0 to infinity, then I would be having a quantity like this, negative 1 over t of e raised to the power of negative p times t. The limits are 0 to infinity, which is negative 1 over t. If I were to place the upper limit, I would get 0. If I were to place the lower limit, I would get 1. So that would be 1 over t. But I don't want just 1 over t. I would like to produce e raised to the power of negative st. So in order to be able to have e raised to the power of negative st, what I would do is, instead of having the lower limit as 0, I would now have the limit as s to infinity e raised to the power of negative p times t times dp. Of course, the outcome is going to be e raised to the power of negative pt divided by negative t, but the limits in this case will not go from 0 to infinity as it did in the previous case. It will be heading from s to infinity. Now, if I were to substitute, in other words, take this negative 1 over t out and have this e raised to the power of negative pt with the limits stretching from s to infinity, I would be applying the limits. So that would give me, if I apply the upper limit, this is going to be 0. I'm applying the lower limit, I would get e raised to the power of, in place of p, substitute s, so this is going to be st. That subsequently will give us e raised to the power of negative st divided by t. So we can now safely use, if I were to have, this implies, if I were to use integral s to infinity e raised to the power of negative pt times dp, I can now have a value of e raised to the power of negative st divided by t. Now I would be using this result. Now how are we going to use this result? Let us start. Start off with this Laplace transform of f of t now. To begin with, we know that this is equal to f of s. Now if I were to write the definition, this is going to be integral 0 to infinity e raised to the power of negative st times f of t times dt, which is equal to capital F of s. Now if I were to replace s by p, then I can rewrite this as integral 0 to infinity e raised to the power of negative p times t f of t times dt is equal to f of p. Now what I wish to do, in the previous case we used the differential operator on both sides. So in this case we would be integrating both sides with reference to p. So I would like to have an integration sign there. The limits are stretching from s to infinity followed by integral 0 to infinity. The variable under consideration is is p, so it's going to be e raised to the power of negative pt times f of t times dt times dp is equal to integral s to infinity f of p times dp. I'm going to rewrite the left side in this following way. So this is going to be integral 0 to infinity followed by integral s to infinity e raised to the power of negative p times t times the operator dp. That would be the required, because we are integrating with reference to p, followed by my f of t times dt. And on the right side it's integral s to infinity capital F of p times dp.
Now this, we have already got this, right? Integral s to infinity e raised to the power of negative pt times dp. We have achieved that result to be as, now let me place this integration 0 to infinity. This is going to be e raised to the power of negative st divided by t, followed by f of t times dt is equal to integral s to infinity of f of p times dp. So this is a nice result that we can use. So let me state the result. So if we are given integral 0 to infinity e raised to the power of negative st times f of t over t times dt, this is nothing but integral s to infinity f of p times dp. So we find the Laplace transform and then we integrate. So let us do a question related to this. First we can rewrite one more step. So Laplace transform of f of t over t is equal to integral s to infinity f of p times dp. So that completes this proof. Students, today we will be learning and understanding the very useful concept called as Laplace transform of derivatives. Now this is very critical and important because it gives you the tool to solve differential equations. Now why differential equations are important? Because they find their application in almost all branch of science and engineering, including computer sciences and as well as in big data analytics, from facial recognition to the smallest or to the ignorable bacterial growth. You can name anything for that matter. So all of these applications that are connected with science and technology can only be solved with the understanding of differential equations, and these differential equations can only be reduced to solvable solutions by Laplace transforms. So having mentioned that, let us proceed on. So the topic is Laplace transform of derivatives. So let me state the definition. If we are given this Laplace transform of f of t is equal to f of s and f dash of t is continuous, that's critical, then the Laplace transform of f dash of t is equal to s times Laplace transform of f of t minus f of 0. This is also written as s times capital F of s negative f of 0. Right? You can either write it like this: Laplace transform of f of t, this is the function that is given, or you can write it as s times capital F of s followed by negative f of 0. So we will be first learning how exactly we can prove this. So that's very critical. So foremost, what we will have to do is we will have to first consider the left hand side. So what is in the left hand side? Consider the left hand side. The Laplace transform of, let me write it like this: Laplace transform of f dash of t is integral 0 to infinity e raised to the power negative st f dash of t times dt. We got this. Now what I'm going to do is I'm going to be taking my u to be as e raised to the power of negative st. This is my u. And my dv, I'm going to be taking it as f dash of t times dt. Now I'm going to differentiate u, I get du. I'm going to differentiate this quantity. This is going to be e raised to the power of negative st. The differentiation is with reference to t, so the coefficient of t is negative s, substitute that, times dt. Now in this case I would have to integrate, because my intention is to get rid of this differentiation. So integral of dv will give me v, integration of this quantity f dash of t dt will give me f of t. That's it. Fair enough. So after performing this, let us move on to use it in the formula. What is the formula? Integration by parts. Okay, integration by parts tells us integral u dv is equal to uv negative integral v du. This is the formula we've got. So using the values of u, v, du, dv, if I were to take this as 2 can be returned as, rewritten as, so u, what is my u? E raised to the power of negative st, that's my u. Dv, my dv is f dash of t times dt. There's an integral sign, so place the integral. The limits are from 0 to infinity, right? So this is what we are trying to solve. And on the right side, my u is e raised to the power of negative st. My v is f of t. The limits are 0 to infinity. Negative integral. Limits are 0 to infinity. My v is f of t. My du is negative. I want to write this quantity of negative s e raised to the power of negative st. Of course, I will place my dt here. My v is f of t. So I substitute the upper limit. This has to be s here, right? So e raised to the power, my t is 0, so it's going to be negative s times of 0, because t is a variable, times f of 0, right? So you can see the s there, because I'm substituting the values for t. So followed by negative times negative is positive integral s. This variable that we are using to integrate is t, so I can take s out. So that would give me e raised to the power of negative s times t, f of t times dt. Now this is going to be 0. Now e raised to the power of negative s times 0 will give me 0. That's going to be 1. So I get a negative f of 0 followed by s times. Now what is this integral e raised to the power of negative st times f of t dt? This is nothing but our favorite Laplace transform of the function f of t. If I were to rewrite this is going to be equal to s times Laplace transform of f of t negative f of 0, or I can rewrite this as s times capital F of s negative f of 0. Now what is on the left hand side? The left hand side, we started with this integral 0 to infinity e raised to the power of negative s times t excuse me, times f dash of t times dt. So this is, let me write that down, integral 0 to infinity e raised to the power of negative st f dash of t times dt. This can also be written as Laplace transform of f dash of t, right? So you got a beautiful result that will come in handy. So that is this proof, students. I hope you understood this. Let's move on. Students, we are given this question to find the Laplace transform of f double dash of t. So from definition, what can we write? So this is what is required. So I'm going to give you the solution over here. Solution from the definition of Laplace transforms. we know that. So what do we know? We know that Laplace transform of f double dash of t is equal to integral 0 to infinity e raised to the power of negative st times f double dash of t times dt. Now what I would do is I would be integrating. We will use integration by parts. So that would mean I would take u to be equal to e raised to the power of negative st, and my dv I'll take it to be as f double dash of t times dt. I differentiate this quantity, I would get du is equal to differential of e raised to the power of negative st. The differentiation is with reference to t, so it's going to be e raised to the power of negative st. The coefficient of t is negative s, place that, multiplied with the differential operator dt. Now in this case of dv, just integrate both sides. Integral of dv will give you v. Integral of f double dash of t dt would give you, one differentiation will be removed, so it's going to be f dash of t. That would be the outcome that you have got. So let me box this off. So I got a u, I got a v, I got a du, I've got a dv. So let me write the dv down. So dv is equal to f double dash of t times dt. Now we will all be using these quantities. So we know that integration by parts formula. So what is that? It's nothing but integral u dv is equal to uv negative integral v du. So I would be using the values of u. U is e raised to the power of negative st times my dv is f double dash of t times dt. Place the integration sign, limits are 0 to infinity. My u is e raised to the power of negative st. My v is f dash of t. The limits are 0 to infinity followed by a negative sign. My v is f dash of t. I don't want to place it as it now. Du is negative s e raised to the power of negative st times dt, and my v is f dash of t. Now I substitute the upper limit. If I substitute the upper limit infinity, this is negative infinity, that is going to be 0, followed by, I substitute the lower limit, it's going to be 1, so this is going to be f dash of 0, followed by negative times negative will give me positive. Now I got integral, of course the limits are 0 to infinity, so it's going to be 0 to infinity. I take the s out, this is going to be e raised to the power of negative st f dash of t times dt. Okay, now what is this value? What is this value? You see that we have got this value here, s times Laplace transform of f of t minus f of 0, so we can use that there. So if I were to rewrite this, this is going to be equal to negative f dash of 0 positive s times, so s into capital F of s minus f of 0, small lowercase f of 0. So rewriting, this is equal to negative f dash of 0 positive s squared of capital F of s minus s into f of 0. Now if I were to rewrite this again, I would like to rewrite this again as equal to
I would like to start with the higher power of s, so it's going to be s squared of capital F of s negative s into the lowercase f of 0 minus f dash of 0. What is this? This is Laplace transform of f double dash of t. So that's the solution for this question, students. So now the students, the most important MIQ, which is known to be as the most important question. What if they ask you to find the Laplace transform of f triple dash of t? Now, what if they ask you to find the Laplace transform of f fourth differential of t, and so on and so forth? So, if they ask you Laplace transforms of f triple dash of t, you cannot be indulging in solving these things because it will take a lot of time. Depends upon the order that they give. So, for that, clearly we know, let me just show you this. The Laplace transform of f double dash of t is equal to, we started off with this result, s squared times Laplace transform of f of t. You can write it either like this or you can write capital F of s. It doesn't matter. So I'm going to start off using this small f of t followed by a negative. What we did, or in other words what we got, is that we got a s followed by f of 0, and the last term was f dash of 0. So why am I writing this? I'm writing this for your observation. So we started with degree 2 because we are dealing with double derivative, and the degree of s happens to be reduced when it moves to the next term, and similarly when it moves again, its degree is again reduced. So we start with 2 and then we have this 1, the power of s is 1 here, and then the power of s is 0 here. So that is the catch. So the highest differential, whenever it is 2 or 3, this is going to start with that degree, and the first quantity is always going to be the Laplace transform of the parent function. In this case it's f of t. So if I were to be given Laplace transform of f triple dash of t, then I would start with s cubed, then I would find the Laplace transform of the parent function, which is f of t, and then I will reduce s by a degree, so it's going to be s squared. Then I will have to calculate f of 0. Again I will reduce this degree, it's going to be s now. Now you can clearly see f of 0, when it moves to the next term, gets a differentiation. So similarly, when over here, when we move to the next term, you place a derivative there, and now reduce the degree or the exponent value for s, that's going to be s0. Increase the differential for f, that's going to be f double dash of 0. So this is going to be for the third differential. Now in general, if they ask you to find the Laplace transform of say f of n t, and that would be, you have to start with the first degree, that's the first value n, so it's going to be s of n, and Laplace transform of the parent function, that's f of t, followed by, as I mentioned to you, reduce the degree by 1, that's going to be s of n minus 1, followed by f of 0. We start with like the original function, taking the value at 0, and then reduce it again. It's going to be s of n minus 2. Now place a differential f dash. Now you move on, reduce it again, n minus 3, place a double differential 0, and then you move on, reduce it again, place one more differential, and following it up, final term, the last term would be a negative f of n minus 1 of 0. So that would be the last term. So this is the nth term. How exactly you can implement the formula if the differential is n? So that completes our formula deduction when it comes to obtaining the Laplace transforms of differentials. Students, we will move on. Students, in this class we will be learning Laplace transforms of integrals.
having studied the Laplace transforms of derivatives, it becomes imperative that we know and understand how to also calculate the Laplace transforms of integrals. And having mentioned this, let me start off with the definition. Now, if we were given the Laplace transform of the function f of t to be equal to f of s, then the Laplace transform of f of t, if it is in this fashion, integral 0 to t f of t dt, is equal to 1 over s times Laplace transform of f of t. This can also be written as 1 over s times f of s. And on the left you got Laplace transform of integral 0 to t f of t times dt. So this is a very important result. Now the question comes, how are you going to prove it? So we have to establish the proof for this. So that's exactly what I'm going to do. Proof. So foremost, what I would do is I would just take, let g of t is equal to integral 0 to t f of t times dt. Now differentiating both sides, we get, so what do you get when you differentiate both sides? Differential of g of t will give you g dash of t. When you differentiate the right hand side, the integral and the differentiation gets cancelled out, giving us f of t. Now when t is equal to 0, we see that g of 0 is integral 0 to 0 f of 0 times dt. I don't want to change anything else further than that. So this is 0. So g of 0 is equal to 0 because the limits are stretching from 0 to 0. So having got that, what I wish to do is I would like to take Laplace on both sides. Taking Laplace transform on both sides, we get, so this is going to be Laplace transform of g dash of t is equal to Laplace transform of f of t. Now what is Laplace transform of g dash of t? Okay, now this is s times Laplace transform of g of t negative g of 0 is equal to Laplace transform of f of t. Now this is rewritten as Laplace transform of, what is g of t? G of t is integral 0 to t f of t times dt. G of 0 is 0. This is Laplace transform of f of t. Now if I were to rewrite this, I'm going to rewrite this as s times Laplace transform of integral 0 to t f of t times dt is equal to 0 can be dropped. I get a Laplace transform of f of t. Now I want to push this s down here, so that would mean I get a Laplace transform of integral 0 to t f of t times dt is equal to 1 over s Laplace transform of f of t. This can be rewritten as 1 over s capital F of s. The left you get Laplace transform of integral 0 to t f of t times dt. So this is a very important result. Now this is the proof. You see that? So you can state that hence proved. Students, we are given this question. We are expected to evaluate, or I should say find the Laplace transform of e raised to the power of negative t, that is multiplied to integral 0 to t sine t divided by t times dt. So foremost, what I wish to do is I wish to find the Laplace transforms of sine t over t. Now I know that the Laplace transform of sine t is equal to 1 over s squared positive 1, and I also know that by definition this is going to be integral s to infinity f of p times dp. Now this is actually f of s, right? Now if I want to write this for f of p, then this is going to be equal to 1 over p squared positive 1. So it doesn't matter what you're using here as long as you know the formula. So this is rewritten as integral s to infinity. So the Laplace transform has to be placed here. So that's going to be 1 over p squared positive 1 times dp. Now if I were to integrate this, this is going to give me tan inverse of p. The limits are s to infinity. I substitute the upper limit. I would get tan inverse of infinity followed by the lower limit, which is going to be tan inverse of s. Now tan inverse of infinity is going to give me pi over 2 negative tan inverse of s. Okay, now I wish to draw your attention to a result which I already know, which is tan inverse of s positive cot inverse of s is equal to pi over 2. So from here I can rewrite this as cot inverse of s is equal to pi over 2 negative tan inverse of s. So using this can be rewritten as cot inverse of s. So on the left I have Laplace transform of sine t over t. So now what I'm going to do is I would have to use this value over here. So let's do that. So now what we need to do is we need to calculate the Laplace transform of integral 0 to t sine t over t times dt. Now what is this? This is nothing but, I can use the formula, right? What is the formula? This is the formula I will be using. So this is nothing but 1 over s times f of s, right? So we are actually looking for the Laplace transform of sine t over t. Now what is that equal to? That is equal to cot inverse of s. Now the question wants us to find Laplace transform of e raised to the power of negative t. So hence the Laplace transform of e raised to the power of negative t integral 0 to t sine t over t times dt is equal to, I will write this directly. So this is going to be the Laplace transform of e raised to the power negative t integral 0 to t sine t dt over t. So if I take a shift of negative 1 units, this is going to be 1 over, in place of s I need to substitute s positive 1, and for cot inverse of s is going to be s positive 1. So this is the final solution for this question. Now I would like to show you all one important variation to the same question. Now instead of this question being given like this, what would you do if they gave the question in this fashion to find the Laplace transform of integral 0 to t e raised to the power of negative t sine t over t times dt. Now the difference between problem 31 and 32 is that e raised to the power of negative t occurs before the integral. In this case it is part of the integrand. So there is a small change in the solution. So foremost what we will do is we will start off by finding the Laplace transform of sine t over t. Now we know that this is nothing but integral s to infinity f of p times dp, and that the f of p
capital F of p is 1 over p squared positive 1. So we would substitute that there and we would get s to infinity dp over p squared positive 1, which when we substitute the limits, before we could do that we would have to write the output, which is tan inverse of p. The limits are s to infinity. When we substitute the upper limit, we get tan inverse of infinity negative tan inverse of s. Tan inverse of infinity is pi over 2 negative tan inverse of s. I would like to use the result that tan inverse of s positive cot inverse of s is equal to pi over 2. Because of this, I can rewrite this as cot inverse of s is equal to pi over 2 negative tan inverse of s. Now because of this, if I were to take this as 2, I can rewrite 2 to be as cot inverse of s. So this is nothing but a Laplace transform of sin t over t. Now from here onwards, this means the Laplace transform of e raised to the power of negative t sin t over t can be written as the shift is taking place. So that would mean cot inverse of s would become cot inverse of s positive 1. That is the change we will have to incorporate. So we have obtained this. Now let's look into the question. So we need to obtain the Laplace transform of the integral. So therefore the Laplace transform of the integral. Say we know the result, right? We know that. Instead of saying therefore, I'll say since we know that integral Laplace transform of integral 0 to t f of t times dt is equal to 1 over s capital F of s. This means the Laplace transform of integral 0 to t e raised to the power of negative t sin t over t is equal to 1 over s f of s. What did we get? It's nothing but cot inverse of s positive 1. So this is the solution. So you can see there is a difference between the previous question and the question that we have just finished. So the all important point is observation. You have to be observant of the question, where the quantities or where the functional attributes occur. Thank you, students. Students, we are expected to find the Laplace transform of integral 0 to t times e raised to the power of negative t sin t times dt. Now first what I would do is I would first find the Laplace transform of sin t. Now we know that this is 1 over s squared positive 1. Next I would find the Laplace transform of t times sin t. So club t with sin t, it's product, so we can do that. So don't take e raised to the power of negative t with sin t. You wouldn't be able to achieve the result in a simplistic fashion. So that's the reason I'm taking Laplace transform of t times sin t. So that would mean negative 1 times d over ds, because s is the variable which I'm using here, times Laplace transform of sin t. So we've already looked into this. So this can be rewritten as negative d over ds. I know Laplace transform of sin t, which is 1 over s squared positive 1. I prefer to use the UV method of differentiation. Let me write that down. D differentiating u over v would give me v times u dash minus u times v dash divided by v squared. So my v is s squared positive 1, you raised to the power of 2. So s squared positive 1, differentiation of u is going to be 0 followed by a negative sign and differentiation of v dash. My u is 1. So when I differentiate s squared, I will get 2 times s. So this is rewritten as negative 2 times s divided by
s squared positive 1 raised to the power of 2. So let us rewrite that. So this is equal to negative of d over ds of this quantity gives me 2 times s divided by s squared positive 1 raised to the power of 2, which is equal to 2 times s divided by, I prefer to write it as 1 positive s squared raised to the power of 2. So this is what we have got for Laplace transform of t times sine t. Okay, so having got this, we will have to find, now apply the shift and get the result. So now, hence, Laplace transform of e raised to the power of negative t times sine t. So the shift is negative 1 unit. So when you are applying it, it's going to be 2 times of 1 positive s divided by 1 positive s raised to the power of 2. The whole quantity is raised to the power of 2. This is what you've got. So you can expand it or you can rewrite it as it is. So I'm just going to write it as 2 times of 1 positive s. Okay, I don't want to change how the s looks, so let it be like that. So when I expand it, 1 positive, this is going to give me s squared positive 2 times s positive 1 raised to the power of 2. This is equal to 2 times of 1 positive s divided by s squared positive 2 times s positive 2 raised to the power of 2. This is my Laplace transform of e raised to the power of negative t times sine t. So now the question comes, therefore I need to obtain the Laplace transform of integral 0 to t times e raised to the power of negative t sine t times dt. Now by definition, this is equal to 1 over s times f of s, right? So hence rewriting, this is equal to 1 over s. My f of s is going to be this entire quantity, so write that down. So 2 times of 1 positive s divided by s squared positive 2s positive 2 raised to the power of 2. So this is my Laplace transform of integral 0 to t times e raised to the power of negative t sine t dt. So we will move on to the next question, students. Students, we are given this question, Laplace transform of e raised to the power negative t times integral 0 to t times cos t dt has to be found out. So foremost, what we will do is we will consider the Laplace transform of cos t. What is that? That's nothing but s over s squared positive 1. And next, Laplace transform of t times cos t, and that is nothing but negative 1 times d over ds of this quantity, which is nothing but f of s, which is going to be equal to negative 1 times d over ds of s over s squared positive 1, which is negative d over ds of s over s squared positive 1. So we need to obtain the differentiation of this. So that is nothing but negative. I would be using u over v method. So differentiating u over v would give me v times u dash minus u times v dash over v squared. This is the formula. So using this formula, I would now have s squared positive 1 times differentiation of s, that's 1, negative s times differentiation of s squared positive 1 will give me 2 times s. This has to be divided by s squared positive 1 raised to the power of 2. This is equal to negative sine s squared positive 1 negative 2 times s squared divided by s squared positive 1 raised to the power of 2. This is equal to negative s squared added with negative 2s would give me 2s squared would give me negative s squared positive 1 divided by s squared positive 1 raised to the power of 2. Now I can take a negative sign out. So if I were to take a negative sign out, this will become positive, and I can write that as s squared negative 1, isn't it? If I were to take this negative sign out, this would become positive, but this one would become negative. So that has to be divided by s squared positive 1 raised to the power of 2. And what is this? This is Laplace transform of t times cos t. So now the all important action is we need to integrate this. So let's do that. We also know that Laplace transform of integral 0 to t times cos t dt is equal to 1 over s times f of s. So in this case we have just obtained the transform here, Laplace transform. So that's going to be 1 over s times f of s is going to be s squared negative 1 divided by s squared positive 1 raised to the power of 2. So the question is Laplace transform of e raised to the power of negative t times the integration. So let me write that down. Hence Laplace transform of e raised to the power of negative t times integral 0 to t times cos t dt is equal to a shift of negative 1. So that means s is moving from s to s positive 1. This is the shift that is taking place. Okay, so let me place this in the box. So that would mean the Laplace transform would be s positive 1 raised to the power of 2 negative 1 divided by s positive 1 times s positive 1 raised to the power of 2 positive 1 raised to the power of 2. So this is the final answer. If you want to expand it, you can expand it. And however, if you choose to expand, you can just expand this. This is going to give you s squared positive 2 times s positive 1 negative 1 divided by s positive 1 times, if I were to expand s positive 1 whole square, that would be s squared positive 2 times s positive 1 raised to the power of 2, which is equal to s squared positive plus 1 negative 1 gets cancelled, giving me s squared positive 2s divided by s positive 1 times s squared positive 2s positive 2 raised to the power of 2. So this is the solution for this question, students. So we move on to the next one. Students, we are given an application question. Laplace transform of t times sine omega t is given to be as 2 omega s divided by s squared positive omega squared raised to the power of 2. We are expected to find the Laplace transform of omega t cos omega t positive sine omega t. Now clearly from this question, let me write that down. From the question, we know that f of t is equal to t times sine omega t. Also, if I were to differentiate this, I would get, I'm going to use uv method. So it's going to be u times v dash positive v times u dash. So by this differentiation is going to be t times differential of sine omega t is going to give me cos omega t. The difference, the quantity with t is omega. So if you differentiate this, you will get omega there. Positive v, my v is sine omega t, and the differentiation of t would give me 1. So this can be rewritten as omega t times cos omega t positive sine omega t. Now if you were to observe the question exactly wants us to find the Laplace transform of this. So this is my f dash of t. Okay, so what is required? Required is to find the Laplace transform of f dash of t. But we know that, what do we know? We know that Laplace transform of f dash of t is equal to s times f of s minus f of 0. So we would have to, hence we will have to find f of s. What is f of s? Laplace transform of the function. What is that? That's nothing but f of t. So what is f of t? F of t is this. So it's Laplace transform of t times sine omega t. But what is t times sine omega t? It's Laplace transform of 2 times omega s. In fact, I don't need to write this as Laplace because this is the Laplace transform, right? So this is equal to 2 times omega s divided by s squared positive omega squared raised to the power of 2. So all of these things gives us f of s. So hence Laplace transform of f dash of t is equal to s times my f of s is what? 2 times omega s divided by s squared positive omega squared raised to the power of 2 negative f of 0. Now let me work that out here. Given f of t is equal to t times sine omega t, so therefore f of 0 is 0. So this is going to be 0. This is equal to 2 times omega s into s would give me s squared divided by s squared positive omega squared raised to the power of 2, which is my Laplace transform of f dash of t. Students, we are given another application problem. If Laplace transform of t times sine omega t is equal to 2 omega s divided by a squared positive omega squared raised to the power of 2, we are asked to find the Laplace transform of 2 times cos omega t negative omega t times sine omega t. So foremost, from the question we know that, or I can say we observe that f of t is equal to t times sine omega t, right? So the Laplace transform of the function is what is being given. So from here, if I were to differentiate both sides, differentiating both sides, we get, so on the left it's going to be f dash of t. On the right hand side we have already obtained the differentiation, so let me just show that. F dash of t is this, so I'm going to use that result here. F dash of t is omega t times cos omega t positive sine omega t. Now I would like to differentiate this again. So differentiating the above term again, we get, so what do we get? On the left it's going to be f dash of t, in fact it's f double dash of t. On the right hand side, now let me use this space. I've got omega t and a cos omega t, and I will have to differentiate this with reference to t. So my u is omega t and my v is cos omega t. I differentiate this, I get omega. I differentiate this, I get sine omega t. Of course there is a negative sign, and the differentiation of omega t would give me omega. So my uv, applying uv method, is going to be u times v dash plus v times u dash, which is going to give me my u omega t and my v dash
negative omega times sine omega t positive cos omega t times my u dash is going to give me omega. So I can rewrite this as negative omega times omega is omega squared times t times sine omega t positive omega times cos omega t. This is my uv, okay, by applying uv method. So instead of this, when I differentiate this, I would be getting negative omega squared times t sine omega t positive omega times cos omega t plus differentiation of sine, that's going to be cos omega t, differentiation of omega t would give me omega. So this is my double differential. So now I can add these two quantities and I can write it as 2 times omega cos omega t negative omega squared t times sine omega t, which is my f double dash of t. So we are getting what we want, but with an addition, or I would say with an extra omega. It's not going to stop us from achieving the result. So therefore, hence, Laplace transform of f double dash of t is going to be equal to s squared of f of s minus s of f of 0 negative, in fact the degree of s drops, so it's going to be f dash of 0. That's it. So this is the formula we will be using. Now my f of t, okay, since f of t is t times sine omega t, my f of 0 is going to be 0 and my f dash of 0, my f dash of 0 is what? See, I need to substitute 0. This is going to be 0, this is going to be 0, so this is going to be 0. So this is to show why I'm getting f of 0 is 0 and f dash of 0 is 0. So this is going to be equal to s squared times f of s, all these terms are going to be 0, 0, 0, giving me just s squared of capital F of s. This is what I have got now. On the left hand side, it's going to be Laplace transform of f double dash of t. But what is f double dash of t? Let me substitute that value. So that's going to be Laplace transform of 2 omega cos omega t negative omega squared t times sine omega t, which is equal to s squared. But what is f of s? Capital F of s. That's nothing but the Laplace transform that we have been given, isn't it? This is the transform, because f of s is what? Let me write that down. Since f of s is nothing but Laplace transform of f of t, right? And my f of t is t times sine omega t, and it's given. What is given? Laplace transform of t times sine omega t is given to be as 2 omega s divided by s squared positive omega squared raised to the power 2. So this is all for your understanding. So substitute that value. So that's going to be s squared times 2 times omega s divided by s squared positive omega squared raised to the power of 2. Now on the left we have got 2 omega cos omega t negative omega squared t times sine omega t. Now clearly you see there's omega here on the left, on the right there's omega here, so we can remove that. So this would mean the Laplace transform of 2 times cos omega t negative omega times t times sine omega t is equal to 2 times omega gets dropped, so I get 2 times s cubed over s squared positive omega squared raised to the power of 2, which is the final answer. In fact, that is what is asked, right? Just make the observation here. This is what is asked, and this is exactly what we have got. So we'll move on to the next question, students. Students, we got this question. The Laplace transform of 2 times root of t over pi is given to be as 1 over s raised to the power 3 over 2. We are expected to find the Laplace transform of 1 over root of pi times t. So foremost, what we are given, so this is the solution. We are given that Laplace transform of 2 times square root of, the 2 is a product multiple, t over pi is equal to 1 over s raised to the power 3 over 2. So this is given. So from here, what do we understand, or from here what do we infer about the function? So I can clearly see that f of t is equal to 2 multiplied with, I'm going to write this as root of t divided by root of pi. This is my f of t. Now let us find f dash of t. So I would say differentiating both sides, we get, so differential of f of t would give me f dash of t. Now differentiation of 2 times, 2 is a constant, of course we are expected to differentiate only t, so let me use the space here. So this is nothing but 2 times t raised to the power of half. Of course you got a pi there with the square root sign. Now if I were to differentiate this, so I want to differentiate this quantity. So if we were to differentiate this, this is going to be equal to 2 over root of pi. We don't have to do anything for that. So this is going to be 1 over 2 times t raised to the power of 1 over 2 negative 1. And that is equal to 2 over root of pi. I have to place the constant, and this is t raised to the power of half negative 1 will give me negative half, and I can rewrite this by cancelling the constant, and I've got 1 over root of pi. This is t raised to the power of negative half, which can be rewritten as 1 over root of pi times root of t. What is this? This is differentiating 2 over root of pi times t raised to the power of half. So this is what I get. So let me place that. So that is going to be 1 over root of pi times root of t. Now let me find the Laplace transform for f dash of t. Hence, the Laplace transform of f dash of t is going to be s times capital F of s minus f of 0. Right, this is the formula we will have to use. You might be wondering, why am I taking the Laplace transform of f dash of t? Why the necessity arises? Simple. If you were to observe the question wants us to find Laplace transform of 1 over root of pi t. And where could I get that 1 over root of pi t? Simply by differentiating the function. When I differentiate f of t, I get what is inside the parenthesis. So that's a reason for me showing you the f dash of t value. Okay, having mentioned that, we are now left to find the Laplace transform of 1 over root of pi times root of t, which is equal to s times, this is s, f of s. What is f of s? Now let me just show it to you. F of s is nothing but the Laplace transform of f of t. Right? So that would mean we would have to go to the question and check it out. What is that? Because f of t is 2 into root of t divided by root of pi. And this Laplace transform is already given. So that's going to be 1 over s raised to the power of 3 over 2 negative my f of t is 2 times root of t divided by root of pi. So my f of 0 is going to be 0. So place the value 0. Now what have I got? I've got s over s raised to the power 3 over 2. So if I were to move them up, so it's going to be s raised to the power of 1 negative 3 over 2. That's going to be s raised to the power of 2 negative 3 over 2, which is going to be s raised to the power of negative 1 over 2, which can be written as 1 over s raised to the power of half, which is nothing but 1 over root of s. So the outcome, therefore, Laplace transform of 1 over root of pi times root of t is this. So that completes our study on Laplace transforms of derivatives and integrals. Welcome students. In this class we will be learning to find the Laplace transforms of periodic functions. So foremost we would have to know what is the meaning when we say a function is periodic. So I would like to give that definition here. A function f of t is said to be periodic if there exists some constant capital T which is greater than 0 such that f of t plus that constant gives us the function back, and this is true for all t. So in other words, we are actually looking for that smallest t such that f of t positive capital T is equal to f of t. So this would mean f of t is periodic with period capital T. So that is the basic definition of a periodic function. Now we got different types of periodic functions that are existing. Say for example, if we were to talk about a rectangular wave function, this is a non-sinusoidal waveform and it is periodic and it is piecewise linear and most importantly it is continuous. So if I were to say draw this function, then this function can be defined as follows. Say f of t is equal to positive 1 for all values of t less than lying between 0 and a, and if it is negative 1 for all values of t greater than a but less than 2a. So if you were to graph this function would be, t will be on the x-axis and the region will be between positive 1 and say negative 1. This is positive 1 and negative 1. So for all values, let me just write
the values a, 2a, 3a, 4a. For all values of t between 0 and a, it's positive one. So, and then for values between a and 2a, this would be the region. And similarly for values between 2a and 3a, this would be the region. And then similarly this would be the region, and similarly this is 5a, and this would be a region. So if you were to draw the dashed line, this would be a wave actually. It's a rectangular wave. And so on and so forth. So this wave, this rectangular wave is periodic with fundamental period being equal to 2a. So imagine you've been given questions like this and we are asked to find the Laplace transforms, and the most important point is how is it, or how are we going to obtain it? Because it is imperative for us to understand that when we're talking about the Laplace transform, first we have to know why are we using it? Why do we need Laplace transform? That's an important question. It is imperative that we know that Laplace transforms converts, okay, this is a very important idea, converts functions in time or functions of time into functions in frequency. Okay, so if you're using Laplace transform, you can always convert a function in time domain into a function or functions in frequency domain. So that's the main idea. So this is the main idea. Why are you using it? Now this comes very much in handy. Why? Because whenever we are having a model, whenever we are creating a mathematical model, so when I say mathematical model for an application, so this mathematical model will carry a differential equation, and this differential equation, if it is a linear differential equation, then it would have a lot of coefficients. So using Laplace transforms, we can convert a differential equation with linear coefficients into a linear algebraic equation. Okay, so these are all some basic ideas which I'm giving you here as a recap so that you will be in a position to understand it. Now, if you are handling, say, initial value problem, if you are handling initial value problem, specifically particular solutions of non-homogeneous differential equations. Now these non-homogeneous differential equations are actually periodic. Okay, so the idea comes here is how are we going to solve these non-homogeneous differential equations? That is where this technique which I am going to be showing you comes in handy. So I have done all these things just to justify the use of Laplace transforms on periodic functions. So having said that, let me move on and show you some related illustrations where exactly a periodic function is given to us and we can use the Laplace transforms and extract the solution. So we are given a question: if f of t is a periodic function with period t, then the Laplace transform of the function is given to be as 1 over 1 negative e raised to the power of negative s times capital T times integral 0 to capital T e raised to the power of negative st lowercase t times f of t times dt. So this is a very important result, and this result occurs when the given function f of t is periodic and the periodicity is also given, capital T. So we are going to be proving this particular result. So foremost, this is the proof. So I will start off that we know that Laplace transform of a function f of t is given to be as integral 0 to infinity e raised to the power of negative st times f of t times dt. We know this result. Now since f of t is periodic with period capital T, if I were to take this as 1 can be rewritten as integral 0 to t e raised to the power of negative st f of t dt positive integral t to 2t e raised to the power of negative st f of t times dt positive integral 2t to 3t e raised to the power of negative st f of t dt positive, let me write down the term here, 3t 4t e raised to the power of negative st f of t dt, and it goes up unto the term infinity. So this is what we have got. So now what I'm going to do is from here I am going to arrive at this right hand side of this proof. So let's do that. Now to start off, first let us consider integral t to 2t e raised to the power of negative st f of t times dt. Now what I would like to do is I would like to make a substitution. Let t be equal to some u positive capital T. So from here when I differentiate I would get dt is equal to du, because this capital T is a constant. Now if I were to take this as 3, therefore 3 can be rewritten as integral. I'm not going to do anything with the limits for now. All I'm going to do is I'm going to substitute. In place of small t I'm going to have u positive capital T, and in place of this small t I'm going to have u positive capital T. In place of dt I'm going to have du. So now this is equal to integral. Now let's fix the limits. Now t is the variable that we are having here. So let me work it out here. When small t is equal to capital T, when you substitute here, what happens here? U will be equal to 0. And when small t is equal to capital 2t, what will happen to u? So I place 2t here, and I got a u here, and I got a t here. This is going to be 2t negative t, and this will mean my value of u is t. So I now have limits. In place of t is going to be 0, and in place of capital 2t is going to be t. Now I'm going to rewrite this as e raised to the power of negative s times u, right, followed by negative s times capital T, with the limits are 0 to capital T, f of u positive capital T times du. Now there is the law of indices. So you got something like this, a raised to the power of m positive n. You can rewrite this as a raised to the power of m times a raised to the power of n. So by this law of indices I can rewrite this as integral 0 to t e raised to the power of negative su times e raised to the power of negative s t capital T times f of u positive capital T times du. Now e raised to the power of negative st. So that is actually a constant. So we can always take that out. So I can, because capital T is a quantity, right? So we can do that. So this is going to be e raised to the power of negative su. In fact, I will write it like this: e integral 0 to t. Now this e raised to the power of negative st, we know that capital T is a constant, right? So we can push this out. So let me place it outside the integral. So this is going to be e raised to the power of negative s times t, and this is going to be f of u positive capital T times du. So this is what we have got. Now we know that since f of, or I should say, since function is given to be periodic with period capital T, this would mean f of u positive capital T will be equal to f of u. So that would mean I can rewrite this as negative e raised to the power of this is actually positive e raised to the power of negative s times t integral 0 to capital T e raised to the power of negative s times u. F of u positive capital T is going to be f of u times du. Now u is the functional variable. Now you can clearly see that this is very similar to integral 0 to, it can be any limit for that matter. Okay, in this case we are using t. This is very similar to integral 0 to infinity e raised to the power of negative st f of t times dt. So if you are going to be connecting this with this, you got a u there, you got a t here, you got a u here, you got a t here, you got a u here, you got a t there, right? So I can very well rewrite this, right, by this statement. Okay, so this is going to be equal to e raised to the power of negative s times t, limits are 0 to capital T, e raised to the power of negative s times t f of t times dt. So this will not impact the function anyway, since all we are doing is replacing one variable by the other. So the best way to show this illustration, suppose you got something like this, say integral, let the limits be say a to b, right, and you got x squared times dx. Now this is same as writing integral a to b t squared times dt, because if I were to take, let x to be equal to some t and dx to be equal to some dt, therefore I can rewrite, I'm not touching the limits as yet, I'm just saying I can rewrite integral x squared times dx as, in place of x I'm going to substitute t, so that's going to be t squared, in place of dx I'm going to substitute dt. Now limits when x is equal to a, let me write that down. When x is equal to a, my t will be equal to a. When x is equal to b, my t will be equal to b. So this is going to be a to b, and the same output will result. So that is the contention I'm using here. So by changing u to t, there isn't going to be any impact at all. So what have we done? So hence we have returned integral capital T to 2t e raised to the power of negative s times t f of t times dt to be as e raised to the power of negative s times capital T, limits are 0 to capital T, e raised to the power of negative s times small t or lowercase t f of lowercase t times dt. So we have obtained this result. Now we will have to continue to obtain other values for the integrals. Integral 2t to 3t e raised to the power of negative s times t f of t dt. So my question is, what would this be equal to? Can you guess it from here? So as we have mentioned, you got it correct. So this is nothing but e raised to the power of negative. Here it is just negative st. In this case, this is going to be e raised to the power of negative 2 times s capital T, integral 0 to capital T, e raised to the power of negative st f of t dt. The only thing is that with t, lowercase t being equal to u positive 2 times capital T. Now similarly, if I were to also take the integral 3t to 4t e raised to the power of negative st f of t times dt, then this is going to be e raised to the power of negative 3 times s times capital T, integral 0 to capital T e raised to the power of negative st f of t times dt, with t being equal to u positive 3t, and so on and so forth. So with all these values, we can go back to what we have got, the original function, when we started with Laplace transform of f of t. So I can state it hence, so which was actually integral 0 to infinity e raised to the power of negative st f of t dt. We actually wrote this as integral 0 to capital T e raised to the power of negative st f of t dt, followed by integral capital T to 2 times capital T e raised to the power of negative st f of t dt, positive 2t to 3t e raised to the power of negative st f of t dt, positive 3t to 4t e raised to the power of negative st f of t dt, plus etc. up unto the final limit infinity. So I'm going to have this as it is, 0 to t e raised to the power of negative st f of t times dt, but integral t to 2t, I'm going to substitute this value which you see here. I'm going to use that. So this is going to be e raised to the power of negative s times t, limits are 0 to t e raised to the power of negative st f of t dt, positive. In place of t to integral 2t to 3t, I would be using this value. So it's going to be e raised to the power of negative 2 times st, limits 0 to capital T, e raised to the power of negative st f of t dt, positive. In place of 3t, or I should say in the place of integral 3t to 4t, I'm going to use e raised to the power of negative 3 times st. The limits are 0 to capital T e raised to the power of negative st f of t dt, plus etc. Now what I wish to do is, I would like to take integral 0 to t e raised to the power of negative st f of t dt as a common quantity, as a common factor, and that would give me 1 positive e raised to the power of negative st, positive e raised to the power of negative 2 times st, positive e raised to the power of negative 3 times st, positive e raised to the power of negative 4 times st, plus etc. That has to be multiplied with integral 0 to capital T e raised to the power of negative st f of t times dt. Fair enough. Now I would like to compare this with the expression 1 positive x squared positive x to the power 3 positive etc. This is nothing but 1 negative x raised to the power of negative 1. So if you were to compare this with this, you can clearly see that, we observe that 1 positive e raised to the power of negative s times t, positive e raised to the power of negative 2 times st, positive e raised to the power of negative 3 times st, plus etc.
is actually equal to 1 negative e raised to the power of negative s times t raised to the power of negative 1. Because as you move away, we start with degree 1, degree 2, degree 3, and so on and so forth. So this is what we have got. So I can rewrite, if I were to take this as say sum 4, now just for the sake of understanding, I'm going to rewrite this as 1 positive e raised to the power of negative st, positive e raised to the power of negative st raised to the power of 2, positive e raised to the power of negative st raised to the power of 3, plus etc. times integral 0 to t e raised to the power of negative st f of t times dt. Now this is equal to 1 negative e raised to the power of negative s times capital T raised to the power of negative 1 times integral 0 to capital T e raised to the power of negative s times, this is actually e raised to the power of lowercase t, times t f of t times dt. Now this is equal to, now I can push this down, so this is going to be 1 over 1 negative e raised to the power of negative s times t times integral 0 to capital T e raised to the power of negative s times t times f of t times dt. So this is actually the result that we were looking. So you can say hence the result, or you can say hence proved. Welcome students, we've been given this question: find the Laplace transform of the rectangular wave function given by f of t is equal to 1 for values of t lying between 0 and b, and f of t is equal to negative 1 for values of t lying between b and 2b, with f of t positive 2b is equal to f of t. So clearly we can see that. So let me start off with the solution as follows. We observe that f of t is a periodic function with period 2b. So if I were to draw this function, taking this as 0, b, 2b, 3b, 4b, and etc. so on, and this point to be as say negative 1, and this point to be as say positive 1, between 0 to b the function will actually take the value 1, so that's going to be over here, and between b and 2b the function takes negative 1, so that's going to be over here, and if you were to continue, the function is going to be in this fashion, and then it jumps down over here, and then it proceeds because it's a rectangular wave function. So if you were to connect it, this is what you will be getting. Now clearly you can see at 2b the function rises, so that is the reason the period is given to be as 2b, right? So that would mean t is equal to 2b. So having got this, what we would do is we would write the required Laplace transform, which we already know. We know that Laplace transform of f of t is equal to 1 over 1 negative e raised to the power of negative s times capital T integral 0 to capital T e raised to the power of negative s times t f of t times dt. This is the Laplace transform of a function with f of t being periodic. Since given that f of t is periodic, that is the reason we are using this, right? So having obtained this, let us substitute. Since t is equal to 2b and f of t positive 2b is equal to f of t, if I were to take this as 2, therefore I can rewrite 2 to be as Laplace transform of f of t is equal to 1 over 1 negative e raised to the power of negative 2sb, because t is equal to 2b. So I substitute the value of t. So followed by integral 0 to 2b e raised to the power of negative s times t f of t times dt. So what we are going to do is we are going to take the value of t to be equal to 2b and use it in this Laplace transform. So this is going to be equal to 1 over 1 negative e raised to the power of negative s times of 2b times integral 0 to 2b e raised to the power of negative st f of t times dt. So now what I wish to do is I would like to start off by considering the right hand side. So let me write that down. So this is going to be, I'll need to start off with 1 over 1 negative e raised to the power of, this is going to be 2 times sb with a negative sign, and the limits are 0 to 2b e raised to the power of negative st times f of t times dt. Now we know that the function is periodic and it starts from 0 to b and then from b to 2b, because t is equal to 2b is the period given. So I will actually split this function as 1 over 1 negative e raised to the power of negative 2 times sb. The limits are going to be 0 to b and then from b to 2b. So that's going to be the limits. So in this case it's going to be e raised to the power of negative st. The function between 0 to b, the functional value is 1, so I'm placing it, times dt, and between b to 2b the functional value is negative 1, so I need to place e raised to the power of negative st of negative 1 times dt. Now I can rewrite this as 1 over 1 negative e raised to the power of negative 2 times sb times integral, just for sake of consistency let me write that down, e raised to the power of negative st times 1 gives me e raised to the power of negative st times dt. Now positive times negative will give me negative, so I got integral b to 2b e raised to the power of negative st times dt. Right? Now if I were to integrate this, now let me just show you this. Suppose you have integral of e raised to the power of, say, some ax times dx. We usually use substitution technique, so we would go on to say that let negative ax be equal to some p, and we differentiate, we get a times dx is equal to dp. So from here we can write dx is equal to dp divided by a with the negative sign. So therefore we can rewrite integral e raised to the power of negative ax times dx to be as integral, in place of negative ax I substitute p, in place of dx I substitute dp with the constant being featured outside along with the negative sign. So this is, upon integration, would give me integral of ep, which is e raised to the power of p, but my p is actually negative ax, so we substitute that and we divide it by the constant a with the negative sign, of course with the arbitrary constant. Now why did I do all these things? Just to show you, if I were to integrate e raised to the power of negative ax, the outcome is going to be e raised to the power of negative ax, but the coefficient of x is negative a, so we have to divide it by negative a. So I need to make sure that you understood this logic. So by integrating this, this is equal to 1 over 1 negative e raised to the power of negative 2 times sb, product multiplied with this quantity. So if you were to integrate, of course the limits have to be written, it's going to be 0 to b. When I integrate this, I get e raised to the power of negative st divided by the coefficient of t, that's s, within the limits 0 to b, followed by a negative sign. If I were to integrate this, I get e raised to the power of negative st. The coefficient of t is negative s, so I place it. The limits are b to 2b. So this is what I get. So now I wish to remove the in fact remove the parenthesis so that I don't get confused with the negative sign later on. So it's going to be 1 over 1 negative e raised to the power of negative 2 times SB, and I take the negative sign out, so it's going to be e raised to the power of negative s times t divided by s, limits are 0 to b, negative negative positive e raised to the power of negative st divided by s, the limits are b to b. Now you can substitute the limits first, so that's going to be 1 over 1 negative e raised to the power of negative 2 times sb. If I were to substitute the limits, I would get upper limit e raised to the power of negative s times b divided by s minus the lower limit. If I substitute 0, the numerator will become 1, so it's going to be 1 over s followed by the upper limit e raised to the power of negative 2 times sb divided by s, negative e raised to the power of negative sb divided by s. So this is what I have got. Now I will remove the parenthesis out, so that would give me 1 over 1 negative e raised to the power of negative 2 times sb, open the parenthesis, this is going to be negative e raised to the power of negative sb divided by s, negative negative positive 1 over s, positive e raised to the power of negative 2 times sb divided by s, this is going to be negative e raised to the power of negative sb divided by s. Now I can add these two things. Before I could add, I can clearly see the denominator is s, so I can take that out. So that's going to be 1 over s times 1 negative e raised to the power of negative 2 times sb. So this is going to give me, if I were to add these two things, that is going to be negative 2 times e raised to the power of negative sb followed by a positive 1 followed by e raised to the power of negative 2 times sb. So this is what I have got. Now I can use a negative b whole squared. Now if I were to expand this, I would get a squared negative 2 times ab positive b squared. So using that, I can rewrite the numerator as, first let me place in the denominator, so it's going to be s of 1 negative e raised to the power of negative 2 times sb times, I start with positive 1, then followed by negative 2 times e raised to the power of negative s times b positive, I'm going to write this e raised to the power of negative 2 times sb as e raised to the power of negative sb raised to the power of 2. Now why, and or in other words, how am I able to do this? Because the law of indices clearly states a raised to the power of m raised to the power of n is a raised to the power of m times n. So having this law, if I were to have something like this, a raised to the power of 2x, I can rewrite this as a raised to the power of x raised to the power of 2, which is the same. So if I were to take, just for your understanding, if I were to take, say, a raised to the power of negative sb as to be as some x, then I can clearly rewrite this term as 1 negative 2 times of x positive x raised to the power of 2, right? If I were to take that e raised to the power of negative sb as x, now what is this? This is nothing but 1 negative x raised to the power of 2, but my x is nothing but e raised to the power of negative sb, so it's going to be 1 negative e raised to the power of negative sb raised to the power of 2. So I'm going to use this over here, so this is going to be 1 over s times 1 negative e raised to the power of negative 2 times sb, and over here I get 1 negative e raised to the power of negative sb raised to the power of 2. This is what I get. Now consider the denominator, just check the denominator. The denominator has got 1 negative e raised to the power of negative 2 times sb. Now why not I write it as 1 negative e raised to the power of negative sb raised to the power of 2. Why not I do that, right? So if I were to do that, this is exactly going to be this, by the law of indices, a raised to the power of m raised to the power of n is equal to a raised to the power of m times n. Now if I were to use e raised to the power of negative sb to be as some x, this is going to be 1 negative, in place of e raised to the power of negative sb, I want to substitute x, and that's going to be x squared here, right? There's a 2 there. Now, is it okay if I can write 1 negative x squared as 1 negative x times 1 positive x, because I know that a squared negative b squared is a negative b times a positive b, right? Fair enough, right? So I'm going to rewrite this denominator as, of course there's a s there, we can't do anything with that. So in place of x, all we need to do is substitute e raised to the power of negative sb. So this is going to be 1 negative e raised to the power of negative sb multiplied with 1 positive e raised to the power of negative sb, right? So over here, what have we got? We got 1 negative e raised to the power of negative sb raised to the power of 2. So place that. Now clearly 1 negative e raised to the power of negative sb over here, with the degree being 2 here, can be cancelled with 1 negative e raised to the power of negative sb, isn't it? Because they are the same. So I can drop 1 out. So I would now have 1 negative e raised to the power of negative sb divided by s times 1 positive e raised to the power of negative sb. Now the question comes, how are we going to solve this? Is there a technique to solve this? Okay, so what I'm going to do is I'm going to multiply the numerator by e raised to the power of sb divided by 2. So the numerator and the denominator is e raised to the power of sb divided by 2. So when I do that, I would get e raised to the power of sb over 2. I'm going to write it like this, negative. Now watch here, let me use this particular space here. Now I've got e raised to the power of negative sb over here, that is multiplied with e raised to the power of sb over 2. So actually what are we doing? We are using the concept of indices, a raised to the power of m times a raised to the power of n. I can rewrite it as a raised to the power of m positive n. So this one is actually e raised to the power of negative sb positive sb divided by 2. So what is this exactly? This is equal to, now if I were to take the LCM, I get negative 2b positive sb, it's actually negative 2sb, right? Negative 2 times sb positive sb divided by 2, so which is going to give me e raised to the power of a negative 2sb added with the positive 2sb will give me negative sb over 2. Fair enough, right? So I just did all of this just to show you what happens when I multiply e raised to the power of sb over 2 with e raised to the power of negative sb. So this is going to give me e raised to the power of negative sb over 2, and I divide this by s times e raised to the power of sb over 2, right? So there is a positive sign, and this is same, right? So this is going to give me e raised to the power of negative sb over 2, right? So there's not going to be any change. So we use the same concept here, right? You got a negative, it's something like this. You have a negative r, negative 1, and you add 1 over 2. So what do you get? The outcome is going to be negative 1 over 2. The same concept I'm using here. So you got two terms like this. Now what is this? Does this sound anything similar that we have studied? Okay, of course, because we know that if I were to be given as Shin theta, now Shin theta is nothing but e raised to the power of theta, negative e raised to the power of negative theta, of course that's theta divided by 2. This is Shin theta. And similarly cos theta is nothing but e raised to the power of theta, positive e raised to the power of negative theta divided by 2. But the only change here is we do not have a 2. So what can I do? So let me use the space. So this is going to be equal to, I don't have a 2, so this is going to be 2 times of Shin e raised to the, in place of theta I get sb divided by 2. So this is going to be sb divided by 2 divided by 2 times in, so this is going to be s is there, we can't forget that s. So let me place the s times of cos sb over 2. Right, so I can place it like this. So 2 over 2 gets cancelled. Now Shin and cos is going to be giving me tan, hyperbolic tan, right? Hyperbolic tan sb over 2. So this is what I get. But there is s there in the denominator, so it's going to be 1 over s. So the Laplace transform for the periodic function f of t, which is actually a rectangular wave function, gives us this solution. Thank you, students.
Welcome students, we have been given this question. Find the Laplace transform of a triangular wave function defined by f of t is t for 0 less than equal to t less than equal to a and 2a negative t when t lies between a and 2a. So if we were to represent this function graphically, then we would have something of this fashion. So 0, a, 2a, 3a. So this is a triangular wave function. So it hits the point 0 to a and then it comes back to 2a and then it climbs, it moves up. And then if this point happens to be 4a, then it will hit the 4a point. So this is a rough picturization, right, of the triangular wave function. Now, having given this information, we will have to use the Laplace transform. We know that the Laplace transform of a periodic function to be, what is that we got? We know that L of f of t is equal to 1 over 1 negative e raised to the power of negative s times capital T. The limits are 0 to capital T, e raised to the power of negative st f of t times dt, right? So this is the Laplace transform of a periodic function which we have learned and we have also proved and we know this for sure. Now given that f of t is periodic and has a period of 2a, right? So if I were to take this as 2, hence 2 can be rewritten as, so this is going to be Laplace transform of f of t is equal to 1 over 1 negative e raised to the power of negative, in place of t I will be taking 2a, so t is equal to 2a. So this is going to be negative 2a times s, integral 0 to 2a e raised to the power of negative st f of t times dt. So this is what we've got. So I'm going to be rewriting this as 1 over 1 negative e raised to the power of negative 2 times as. Now the limits are 0 to 2a, so I can divide the limits 0 to a followed by a to 2a. So this is the split I would be using. So with this, I'm going to rewrite this as 1 over 1 negative e raised to the power of negative 2as. The limits 0 to a e raised to the power of negative st f of t between 0 to a. Just check it out. Function takes the value t, so I am going to place the value t times dt positive a to 2a. The function takes the value 2a minus t, so it's going to be e raised to the power of negative st times 2a minus t times dt. So this is what I've got. Now to integrate this, we will use the Bernoulli technique. Okay, so what exactly is the Bernoulli technique? It's called as Bernoulli technique or Bernoulli formula. Now if you are given, say, integral uv dt, then the right hand side is going to be u times v1 negative u dash v2 positive u double dash v3 negative u triple dash v4 plus etc. Now where u dash is the first differential, okay, and u double dash is second differential and u triple dash is third differential and so on. So instead of saying first differential, I can just say where u dash, u double dash, u triple dash, etc. differential quantity of u, and v1, v suffix, right, suffix v2 and v3, they are the integral or integral of quantity v, right? So one gives the differential, the other is the integral. So students, we will be applying the Bernoulli's principle for integral 0 to a e raised to the power of negative st times t dt. So what I will do is I will take my u to be as t and my v to be as e raised to the power of negative st. Now if you were to integrate this is going to be e raised to the power of negative st. The coefficient of t is negative s, and then again integrating v1, I would get e raised to the power of negative st divided by the coefficient of t is negative s, so this is going to become positive s squared. Now differentiating this, u dash is going to be 1. That's it. You don't have to differentiate any further, which will just result in 0. So integrating or integration of this is going to result in me using the Bernoulli's, which will start as u times v1 negative u dash times v2. We don't need anything further than that. The limits are 0 to a. So my u is t times my v1 is e raised to the power of negative st divided by negative s, followed by my u dash is 1 times my v2 is going to be e raised to the power of negative st divided by s squared. So the limits are 0 to a. So we would have to apply the limits, upper limit minus lower limit. So I'll start off with applying the upper limit. So it's going to be a times, of course there's a s there. In fact, I can just place that, followed by e raised to the power of negative s times a, that is for the upper limit, then minus, this is going to be 1 over s squared, I'm still with the upper limit, e raised to the power of negative s times a, this is for the upper limit. Now the lower limit, I place 0 here, the first quantity will give me 0, followed by negative 1 over s squared of e raised to the power of 0. Since t is 0, so that is going to give me a value of 1 there. So this can be rewritten as a times e raised to the power of negative sa divided by s with a negative sign, followed by negative 1 over s squared e raised to the power of negative sa, and I've got a negative positive 1 over s squared. So this is the quantity that I have received for integrating 0 to a e raised to the power of negative st times t times dt. So we will move on to integrating the next term. Now students, I've just rewritten the values that we have got for integrating integral 0 to a e raised to the power of negative st times t times dt. Now we need to integrate integral a to 2a e raised to the power of negative st times 2a negative t times dt. So what I would do is I would take my u to be as 2a negative t and my v to be as e raised to the power of negative st. I integrate this, I get e raised to the power of negative st divided by negative s. I again integrate this, I get e raised to the power of negative st divided by s squared. I integrate this, I get e raised to the power of negative st divided by s cubed with a negative sign. Now, of course, I don't need to go and find V3. It wouldn't be necessary because of the degree of t being 1 here. So I will differentiate first quantity, that's going to be -1, and we don't need u double dash, so u dash alone is enough. So by Bernoulli, it's going to be u times v1 minus u dash times v2. That's what we need. So this is equal to, my u is 2a negative t, my v1 is e raised to the power of negative st divided by s, my u dash is -1 times my v2 is e raised to the power of negative st divided by s squared. So this goes from a to 2a. Now, before I could apply the limits, I can actually change this to positive, right? Negative, negative, that's going to be positive. So I would just rewrite it 2a negative t, and then I will just place -1 over s in the front like this, followed by e raised to the power of negative st. So this is one quantity, and followed by positive e raised to the power of negative st divided by s squared. So this is another quantity, quantity 1, quantity 2, and all of this are subjected to the limits a to 2a. So that's about it. So I apply the upper limit, so that's going to be 1 over s. I apply the upper limit, this is going to be 0, okay, followed by positive, I apply the upper limit, e raised to the power of negative. So in place of t, I substitute 2a divided by s squared. So this is for the upper limit, right? And minus, I apply the lower limit, so it's going to be 1 over s times 2a negative a, that's going to give me a, e raised to the power of negative sa, followed by positive e raised to the power of sa divided by s squared. This is what I've got. So rewriting, I can now have integral a to 2a of e raised to the power of negative st of 2a negative t dt to be as e raised to the power of negative s of 2a divided by s squared, followed by positive a e raised to the power of negative sa divided by s negative e raised to the power of negative sa divided by s squared. So I've got this term. Now the original integral which we started, hence we started like this, right? 1 over 1 negative e raised to the power of negative 2as integral 0 to a e raised to the power of negative st t times dt, positive integral a to 2a e raised to the power of negative st of 2a negative t times dt. This is what we add. Now we know that this value, right, is 1 over 1 negative e raised to the power of negative 2as. This value is going to be negative a times e raised to the power of negative sa divided by s, followed by a negative sign, e raised to the power of negative sa divided by s squared, followed by positive 1 over s squared. This is the value that we got, if you could check back. Followed by, this is nothing but this value that we have here. So just substitute that value, e raised to the power of negative s and 2a, I'm going to write it as 2as divided by s squared, positive a times e raised to the power of negative sa divided by s, negative e raised to the power of negative sa divided by s squared. So we got it like that. So let us see if we can cancel anything. So this is negative a times e raised to the power of negative sa divided by s, and you got positive a times e raised to the power of negative sa divided by s. So these two can be cancelled, and we got negative e raised to the power of negative sa divided by s squared, and negative e raised to the power of negative sa divided by s squared. So I can rewrite this as 1 over 1 negative e raised to the power of 2as. So I can add them up, but I would like to first start with 1 over s squared. This is going to be negative 2 times e raised to the power of negative sa divided by s squared, and then I've got a positive e raised to the power of negative 2as divided by s squared. So this is how I got it. Now what I wish to do is I would like to relate this, okay, to relate this to the expression or the formula a negative b raised to the power 2, which are in fact the best thing would be to relate it with 1 negative a raised to the power of 2. In either case, in the first case you get a squared negative 2ab positive b squared. The second case you get 1 negative 2a positive a squared. So it doesn't matter, but clearly you can see this relation. So I can take that s squared out, so that would be 1 negative, it should be 1 over s squared of 1 negative e raised to the power of negative 2as, and this is 1 negative 2 times e raised to the power of, now let me write it as as, since I'm having as over here. So this is going to be as positive e raised to the power of negative as raised to the power of 2. Okay, now why am I able to do this? Because of the fact that a raised to the power of m times n is a raised to the power of m raised to the power of n. The best way to say that, if you have a term like a raised to the power of 2x, you can actually write this as a raised to the power of x raised to the power of 2. Okay, because of the law of indices lets you to do that. So that is exactly what I'm doing. So if I were to take e raised to the power of negative as to be as x, just for the sake of this question, then I can rewrite 1 negative 2 times e raised to the power of negative as positive e raised to the power of negative as, the whole squared, can be 1 negative 2 times x positive x raised to the power 2. This is nothing but 1 negative x raised to the power of 2, right? So I can rewrite this as 1 over s squared times 1 negative e raised to the power of negative 2 times as times 1 negative e raised to the power of negative, right? Because my x is e raised to the power of, this is s, right? E raised to the power of as. So this is going to be e raised to the power of negative as, and I'm raising it to the power of 2, right? The expression. Now I'm going to rewrite this as 1 over s squared. I can rewrite the term 1 negative e raised to the power of as 1 negative e raised to the power of, it's actually 2as. So I'm going to write it as e raised to the power of as, and that is raised to the power of 2. Of course, in the numerator I got 1 negative e raised to the power of as raised to the power of 2. Now if I were to take the same substitution, e raised to the power of negative as is equal to x, this is going to be, this is, let me write that down, 1 negative e raised to the power of negative as, the whole square. If I were to substitute this substitution, this is going to be 1 negative x squared, which is, can be rewritten as 1 negative x times 1 positive x, right? So with this I can easily rewrite this as 1 negative e raised to the power of as raised to the power of 2 divided by s squared times 1 negative e raised to the power of as times 1 positive e raised to the power of negative as. Fair enough, right? Now 1 negative e raised to the power of as can be cancelled, so that would give me in the numerator 1 negative e raised to the power of as divided by s squared times 1 positive e raised to the power of negative as. Now what I wish to do, I would like to multiply the numerator by e raised to the power of as divided by 2. So this is going to give me e raised to the power of as over 2 negative e raised to the power of, now this is like just show this to you. So this is negative 1 added with 1 over 2 actually. So that would give me negative 1 over 2, right? So when you multiply e raised to the power of negative as with e raised to the power of as over 2, this is going to give you negative as over 2 divided by s squared times, of course you have to multiply and divide, right? So it's going to be as over 2. So this is going to be e raised to the power of as over 2 positive e raised to the power of, same thing, is going to give you negative as over 2. Now what is this? This is nothing but, now if you were to take Shin theta is e raised to the power of theta, negative e raised to the power of negative theta divided by 2. Right? This is Shin theta. So what is this going to be? This is going to be 2 times of Shin a s over 2 divided by s squared times, what is this? This is nothing but cos 2 times. Right? So it's going to be 2 times of cos as over 2. So the 2's can be cancelled, giving you 1 over s squared of Shin as over 2 cos as over 2. That is going to give you hyperbolic tan as over 2. So this is the Laplace transform for the function.
Welcome students, we've been given this question. The half sine wave rectifier function is defined by f of t is equal to sine omega t. In other words, the function is equal to sine omega t for values of t lying between 0 and pi over omega. And the function takes the value 0 for values of t lying between pi over omega and 2 pi over omega. Now we can observe that the function f of t is periodic, but I would like to show that to you. So what I would like to do is, I would like to start off by stating this. Given f of t is equal to sine omega t. Of course, for the values of t lying between 0 and pi over omega. Now, a function can be called to be periodic if I can show that f of t positive 2 pi over omega is equal to f of t. So if this happens, then this would mean that f of t is periodic with t being equal to 2 pi over omega. So this is what we have to conclude if this occurs. So let us start off with this. So I'm going to say consider f of t positive 2 pi over omega. Now f of t is sine omega t, so this is going to be sine omega. In place of t I will be substituting t positive 2 pi over omega. Now what I wish to do, I would like to bring omega inside. So that would mean I will get sine of omega t positive. I cancel omega, I will get 2 pi. Now what is this? This is equivalent to sine of a positive b, which is nothing but sine a cos b positive cos a sine b. So using this is going to be sine omega t cos 2 pi positive sine 2 pi and cos omega t. Now sine 2 pi, this will vanish. Now cos 2 pi is equal to positive 1. So this is equal to sine omega t, which is nothing but f of t. So clearly we see that f of t positive 2 pi over omega is f of t. So we need to do all these things to ensure that f of t is periodic with period 2 pi over omega. So now we need to obtain the Laplace transform of this periodic function. So let's do that. So we can conclude that. So this would mean f of t is a periodic function with period 2 pi over omega. So if you were to draw the graph, this is t, this is f of t, the values are 0, pi over omega, and 2 pi over omega, and so on and so forth. So this is a half-wave function. So it will start like this, it will touch here, then it will hit 0, and then again at 2 pi over omega it will start off like this. So this is a rough half sine curve. So now we will use the definition of the Laplace transform. We know that Laplace transform of f of t, given that, of course this is given that f of t is periodic, we know that this is equal to 1 over 1 negative e raised to the power of negative st integral 0 to capital T e raised to the power of negative st times f of t dt. Now since t is equal to 2 pi over omega, if I were to take this as 2, therefore 2 can be rewritten as 1 over 1 negative e raised to the power of negative s times 2 pi over omega integral 0 to 2 pi over omega e raised to the power of negative st f of t times dt. Now this can be further split as integral 1 over 1 negative e raised to the power of negative s times, in fact I could have written it as 2 pi, okay, I will do that in the next step. So 2 pi over omega integral 0 to pi over omega e raised to the power of negative st f of t dt positive pi over omega to 2 pi over omega e raised to the power of negative st f of t times dt. Now from the question you can see that the function takes sine omega t between, for values of t lying between 0 and pi over omega, but the function takes a value 0 for values of t lying between pi over omega and 2 pi over omega. So this one will vanish. So this would give us 1 over 1 negative e raised to the power of negative 2 pi s over omega integral 0 to pi over omega e raised to the power of negative st times f of t times dt. But however, my f of t is going to be 1 negative e raised to the power of negative pi s over omega. Now since my f of t is equal to sine omega t, I can rewrite this as 0 to pi over omega e raised to the power of negative st times sine omega t times dt. This is what I've got. Now we need to solve this. So now to integrate this, I would be using a very popular formula. So that formula is, I'm going to state it here. So let me do that. So we know that integral e raised to the power of ax times sine bx times dx is e raised to the power of ax divided by a squared positive b squared times a times sine bx negative b times cos bx. So this is a formula. So I would be using this formula. We're supposed to integrate this. Now to integrate this we would be using a known formula. So I will be using this particular integral formula. We know that integral, let me not state the limits, integral e raised to the power of ax sine bx dx is equal to e raised to the power of ax over a squared positive b squared of a times
sine bx negative b times cos bx positive c. So we would be employing this formula to evaluate this. So foremost what I would do is I would say consider integral e raised to the power of negative st times sine omega t dt. Now clearly we see that in place of x we got t, in place of a we got negative s, and in place of b we got omega. So we will have to substitute that. So x is actually t. So this is going to be e raised to the power of negative s times a is negative s and my x is t divided by a is negative s, so negative of s raised to the power of 2 will give me s squared, positive b is omega, so place that. Now a is negative s times sine of b is omega. Instead of x I need to place t followed by omega cos omega. Instead of x I place t. I don't have to place positive c because it's a definite limit. The limits are 0 to pi over omega. So we can substitute 0 to pi over omega and all of these things will be included. Now clearly we see that s squared positive omega squared is constant, so I can take that out, s squared positive omega squared, and I can subject other things to the limit. So let me substitute the upper limit. So this is going to be e raised to the power of negative s times pi over omega, that's the first quantity, times negative s times sine of omega of pi over omega negative omega times cos of omega times pi over omega. This is for the upper limit, so let me place it like this, minus the lower limit, e raised to the power of negative s times 0 times negative s times sine of omega of 0 negative omega times cos of omega times 0. Okay, so this is upper limit minus the lower limit. So let me place it like this and within flower parenthesis. Now this is equal to, let's evaluate this, this is equal to 1 over s squared positive omega squared. Now omega can be cancelled, you will get sine pi is 0, so it goes off. Now we are left with e raised to the power of minus s times pi over omega, with omega gets cancelled, you get cos pi is negative 1, so it's negative omega of negative 1. So that's for the first part, followed by e raised to the power of 0, negative s times 0, this is going to be 0, so that's going to be 1 there. 1 multiplied with, this is going to get vanished, cos 0 is 1, so I get a negative omega of 1, this is what I get. So this term, and I can rewrite this as 1 over s squared plus omega squared e raised to the power of negative s times pi over omega. This is omega followed by negative positive omega. This is what I get. So I can rewrite this by taking omega out. This is 1, omega times 1 will give you first omega, followed by positive e raised to the power of negative s times pi over omega divided by s squared positive omega squared. This is what you get for this quantity. But this quantity, let me show that to you. This quantity is this. I got to take this quantity and substitute here. So let's do that. So therefore hence, let me write that, hence 1 over 1 negative e raised to the power of negative 2 pi s over omega can be written as, in fact it's better I write the integral 0 to pi over omega e raised to the power of negative st sine omega t dt is now equal to 1 over 1 negative e raised to the power of negative 2 pi s over omega. So in place of this I substitute this. So let me place that. That's going to be omega times 1 positive e raised to the power of negative s pi over omega divided by s squared positive omega squared. I can rewrite this by taking omega out, and let me write this like this: 1 positive e raised to the power of negative s times pi over omega divided by s squared positive omega squared times, now I can write 1 negative e raised to the power of negative 2 pi s over omega to be equal to 1 negative e raised to the power of negative pi s over omega, the whole raised to the power of 2. Now how am I able to do that? Because if I got a raised to the power of 2x, I can write this as a raised to the power of x raised to the power of 2 by log indices. Now if I were to take, let e raised to the power of negative pi s over omega to be as some x, then I can rewrite this term as 1 negative x squared. Now 1 negative x squared can be written as 1 negative x times 1 positive x. Now I can rewrite this x as 1 negative e raised to the power of negative pi s over omega times 1 positive e raised to the power of negative pi s over omega. Okay, this is what we can write. So that's exactly what I'm going to do. I'm going to write this quantity as 1 negative e raised to the power of negative pi s over omega times 1 negative e raised to the power of negative pi s over omega. Of course this should be positive, right? Negative and positive. 1 positive e raised to the power of negative s pi over omega and 1 positive e raised to the power of negative pi s over omega, these two things can be cancelled. So if I were to cancel this, I would get omega over, I'm going to write this as 1 negative e raised to the power of negative pi s over omega times s squared plus omega squared. Now what is this exactly? This is the Laplace transform of the function. Okay, that has been given. So this completes the solution to this question, students. Students, we're given this question: find the Laplace transform of a function f of t taking the value e for t lying between 0 and a over 2, and the function takes the value negative e when t lies between a over 2 and a, and we are also given that the function is periodic. So let us start the solution for this question. We are going to say that we know that the Laplace transform of a periodic function f of t to be equal to 1 over 1 negative e raised to the power of negative s times capital T, with the integral stretching from 0 to t e raised to the power of negative st times f of t dt. Now since we are given it's periodic and the period is a, if I were to take this as 1, therefore I can rewrite 1 as 1 over, of course this is equal to the Laplace transform of this function, 1 negative e raised to the power of negative s times a 0 to a e raised to the power of negative st times f of t times dt. I'm going to split this as 1 over 1 negative e raised to the power of negative sa. I'm going to split it as integral 0 to a over 2 e raised to the power of negative st. I'm not going to place the functional value as yet, followed by a over 2 to a e raised to the power of negative st. The functional value I will reserve it. Now clearly we see that when t ranges from 0 to a over 2, the functional value is e. When t ranges from a over 2 to a, the functional value is negative e. So this can be rewritten as integral, let me just place this quantity, 1 negative e raised to the power of negative sa. We have to integrate 0 to a over 2 e raised to the power of negative st. E, I can just place e out, times dt. This is going to give me negative e integral a over 2 to a e raised to the power of negative st times dt, and the parenthesis. So I can take the e out and write the quantity as e over 1 negative e raised to the power of negative sa. The integration is 0 to a over 2 e raised to the power of negative st dt. This is going to be integral a over 2 to a e raised to the power of negative st times dt. So let us check the integration. What happens when we integrate 0 to a over 2 e raised to the power of negative st times dt? This is going to give me e raised to the power of negative st. The coefficient of t is negative s. The limits are 0 to a over 2. Now I can rewrite this as 1 over s with a negative sign, and I substitute the upper limit e raised to the power of negative s times a over 2 followed by a negative sign e raised to the power of 0. So this is going to be e raised to the power of 0 is 1, so it's going to be 1 over s with a negative sign e raised to the power of negative sa over 2 negative 1. I can rewrite it by taking the negative sign inside, and that would give me 1 negative e raised to the power of negative sa over 2 divided by s. Now this has to be placed here, so let me do that. So this is equal to e over 1 negative e raised to the power of negative sa. So I place this quantity 1 negative e raised to the power of negative sa over 2 divided by s. Now I need to evaluate this, so let me use this space over here. So integral a over 2 to a e raised to the power of negative st times dt will give me e raised to the power of negative st. The coefficient of t is negative s. The limits are a over 2 to a. I take this negative s out, so it's going to be 1 over s with a negative sign. I substitute the upper limit, I get e raised to the power of negative sa negative. I substitute the lower limit, e raised to the power of negative sa over 2. And if I were to take the negative sign inside, this would give me e raised to the power of negative sa over 2. Of course there is a s there, but I will place it at the end. For now I'm just taking the negative sign inside, so followed by negative e raised to the power of negative sa divided by s, and this is integral a over 2 to a e raised to the power of negative st times dt. Now instead of this I place this, so it's going to be a negative sign here, and apparently I will have to place e raised to the power of negative SA over 2, followed by a negative sign e raised to the power of negative SA over S. So this is what I've got. Now I need to do the sign evaluation again. I could have not done it over here, but never mind. So this has to be evaluated since I'm looking for some space to evaluate it. Okay, let me use the space here. So this is equal to capital E over 1 negative e raised to the power of negative SA, and opening the parenthesis. So let me write this like this: 1 over S negative e raised to the power of negative SA over 2 divided by S negative e raised to the power of negative SA over 2 divided by S negative negative positive e raised to the power of negative SA divided by S. So this is what I have got. Now you see you got e raised to the power of negative SA over 2, and I get e raised to the power of negative SA over 2. So we can add them both. So what I wish to do is I would use this space over here. So it's going to be e over 1 negative e raised to the power of negative SA. Now if I were to add this, I would get 1 over S. These two can be added, negative SA over 2 and negative SA over 2. That would give me negative 2 times e raised to the power of negative SA over 2 divided by S, followed by a positive e raised to the power of negative SA over S. Now this looks familiar. I can simplify this, and let's do that. I need to go on to a new page. So now we got this relation. What I want to do is I would like to take S out. If I were to do that, I get e over S of 1 negative e raised to the power of negative SA times 1 negative 2 times e raised to the power of negative SA over 2 positive e raised to the power of negative SA. Now if I were to rewrite e raised to the power of negative SA as e raised to the power of negative SA raised to the power, in fact let me divide this by 2. Let me write it like this: divide by 2 and I square it. So this is nothing but a raised to the power of, if I have something like this, a raised to the power of 2m, I can rewrite this as a raised to the power of m whole squared, like this. So that's exactly what I'm doing, because if I were to square it, I would get e raised to the power of negative SA back. So I wish to do that. So I'm going to rewrite this as e over S times 1 negative e raised to the power of negative SA times 1 negative 2 times e raised to the power of negative SA over 2 positive e raised to the power of negative SA over 2. The entire quantity is raised to the power of 2. Now if I were to take, let x be equal to e raised to the power of negative SA over 2, then I'm just showing you on the rough side, then this would be equal to 1 negative 2 times x positive x squared, which is nothing but 1 negative x raised to the power 2, right? So which can be rewritten as 1 negative e raised to the power of negative SA over 2 the whole squared. So this can be rewritten as e over S times 1 negative e raised to the power of negative SA. So it's going to be 1 negative e raised to the power of negative SA over 2 raised to the power of 2, right? Now what I can do with the denominator, now what's the denominator? I can rewrite the denominator as 1 negative e raised to the power of negative SA over 2 the whole squared. Now if I were to use instead of e raised to the power of negative SA over 2 to be as x, this is going to be 1 negative x squared, which can be rewritten as 1 negative x times 1 positive x, which is going to be 1 negative e raised to the power of negative SA over 2 times 1 positive e raised to the power of negative SA over 2. Right? Fair enough. So this is going to be e over s times 1 negative e raised to the power of negative SA over 2 times, so 1 positive e raised to the power of negative SA over 2 for the denominator. In the numerator, I've got 1 negative e raised to the power of negative SA over 2 raised to the power of 2. This is in the numerator. Now I can rewrite this as e times 1 negative e raised to the power of negative SA over 2 multiplied, in fact I don't need to, I can just cancel this one term with the other term, and that would be one term remaining divided by s times 1 positive e raised to the power of negative SA over 2. So we got a beautiful relationship over here. We can't stop here, you will have to simplify it still further. So I'm going to rewrite this as e over s times 1 negative e raised to the power of SA over 2. I'm going to multiply the numerator and denominator by e raised to the power of SA over 4 and divide by e raised to the power of SA over 4. You'll know the reason why I'm doing this. Of course, I got 1 positive e raised to the power of SA over 2. Now this is equal to e over s. 1 multiplied by e raised to the power of SA over 4 will give me e raised to the power of SA over 4 negative. Now you got a negative 1 over 2. Just watch it like this. Negative 1 over 2 with being added with 1 over 4. What would you get? You get 4 negative 2 positive 1, which is negative 1 over 4. This is what you would get. Now why am I adding it? This is nothing but the exponent, right? Now if you were to look into this exponent, if you were to multiply this, you are getting e raised to the power of negative SA over 2 multiplied with e raised to the power of positive SA over 4. So what is this? This is nothing but e raised to the power of negative SA over 2 added with positive SA over 4, which is going to give you e raised to the power of negative SA over 4. That is exactly what I did here, right? So this is going to be e raised to the power of negative SA over 4. And if you were to do the same thing for the denominator, this is going to be e raised to the power of SA over 4 positive e raised to the power of negative SA over 4. And what is this? This is nothing but, we know that Shin theta is e power theta negative e power negative theta over 2. This is Shin theta, but we don't have a 2 here, so this is going to be 2 times Shin of e raised to the power of SA over 4 divided by S over, what is this? This is nothing but cos theta. What is cos theta? E power theta plus e power negative theta divided by 2. This is cos, but we don't have a 2 there, so this is going to be 2 times of cos e raised to the power of SA over 4. The 2 and the 2 can be cancelled. But what is Shin over cos? Shin over cos is nothing but hyperbolic tan e raised to the power of SA over 4. And you got the S there. So this is this is the Laplace transform of the given function. So this completes our study on periodic function, students, and practice makes perfect. Welcome, students. In this class we will be studying about Laplace transform of convolution. Before we could start off with applying Laplace transform to convolution of
functions, we must know what exactly convolution of two functions means. Suppose you are given f star g of t. This is how we represent convolution of two functions. Now this is equal to integral 0 to t f of t negative u times g of u times du. Now this can also be rewritten as integral 0 to t f of u g of t negative u times du. So these two can be used depending upon the question that is asked. So they come in handy. So this is how we define convolution of two functions. Now if we were to be given, say, so in which we are expected to apply Laplace transform for the convolution of two functions, then the outcome is equal to f of s product multiplied with g of s, where Laplace transform of f of t is capital F of s and Laplace transform of g of t is capital G of s. So this is exactly the outcome we will get when we apply the Laplace transform for convolution of two functions. Now we are going to do some problems using these definitions. Students, we are given this question. We are expected to find the Laplace transform of integral 0 to t 3 of t negative u raised to the power 2 times sine 2u times du. Now this is similar to finding the Laplace transform of integral 0 to t of f of t negative u times g of u times du, where f of t negative u is equal to 3 times of t negative u raised to the power of 2 and g of u is equal to sine 2u. So now clearly f of t can be obtained from here. So if I were to take, let t negative u be equal to t, then f of t is going to be 3 times t squared, and if I were to take in this case u to be equal to t, then g of t is going to be sine 2t. Now let us find the Laplace transform of f of t, which is nothing but Laplace transform of 3 times t squared, which is nothing but 3 times of Laplace transform of t squared. Now we know that the Laplace transform of t power n is n factorial divided by of n positive 1. So this is equal to 3 times 2 factorial divided by s raised to the power of 2 positive 1, which is 6 divided by s cubed. So Laplace transform of g of t in this case is going to be Laplace transform of sine 2t, which is equal to 2 over s squared positive 2 squared, which is 2 over s squared positive 4. So therefore the Laplace transform of the convolution 0 to t f of t negative u times g of u du is given as f of s product multiplied with g of s, which is nothing but Laplace transform of f of t times Laplace transform of g of t, which is equal to Laplace transform of f of t is 6 divided by s cubed, and Laplace transform of g of t is 2 over s squared positive 4, which is 12 over s cubed times s squared positive 4. So this is the Laplace transform of integral 0 to t 3 times of t negative u raised to the power 2 sine 2u times du. So this will be the solution. Since we are expected to find the Laplace transform of integral 0 to t u
times e raised to the power of negative 2 of t negative u times du. Now this is similar to, let me write that down, this is similar to finding the Laplace transform of integral 0 to t f of u times g of t negative u times du, which is nothing but f of s times g of s. So we would be using the convolution. So by comparing, clearly we see that f of u is equal to u and g of t negative u is e raised to the power of negative of t negative u. Now if I were to take t negative u is equal to t, then this would mean g of t is e raised to the power of negative 2 times t. Over here, if I were to take u is equal to t, then this would mean f of t is equal to t. So let me find the Laplace transform of f of t. This is going to be 1 over s squared, and the Laplace transform of g of t is 1 over s positive 2. So therefore the Laplace transform of the convolution, which is given as integral 0 to t u times e raised to the power of negative 2 of t negative u times du, is equal to 1 over s squared times 1 over s positive 2, which is rewritten as 1 over s squared times s positive 2. So this is the solution to this question. Students, we are given this question: verify the convolution theorem given that f of t is t and g of t is sin t. So the convolution theorem states that, let me state that, Laplace transform of f star g of t is equal to capital F of s product multiplied with g of s, where the convolution f star g of t is written as integral 0 to t f of t negative u times g of u times du. So this is the definition when you have the convolution of two functions, and the variable under consideration is u. So this is very important. Now what we are going to do is we are going to prove this. This is the subject of contention, okay, with the function f of t being t and g of t being equal to sin t. So foremost, let us consider the left hand side. So we got Laplace transform of f star g of t, which can be rewritten as Laplace transform of, now f star g of t is this integral 0 to t f of t negative u times g of u times du. Now given f of t is equal to t, this means f of t negative u is equal to t negative u, and g of t is equal to sin t. It's given, right? So this would mean g of u is equal to sin u. So if I were to take this as 1, using these in 1, we get, so what do we get? This would be Laplace transform of integral 0 to t f of t negative u, substitute t negative u, and g of u is going to be sin u times du. I can rewrite this as integral t times sin u, so t times sin u du, limit 0 to t, negative integral u times sin u. So u times sin u du, the limits are 0 to t.
Now t is a constant, so take that out. So Laplace transform of t times integral 0 to t sin u du negative. Now we need to apply UV method. So let me write that down again. Integral 0 to t u times of sin u du. Now this is going to be, integral of sin u is going to be negative cos u. The limits are 0 to t. Of course you have a t there. So this is actually a Laplace transform of this quantity. Followed by, now let me use the rough column to perform the integration. So this is integral u times sin u du. Now what we will do is we will take the Leadness rule. So integration by parts. Integration by parts. According to integration by parts, u dv is equal to uv negative integral v du. So we will take the value of u. Apparently we have variables u and du to handle. So I will just take this u to be equal to capital U. So du is going to be equal to du here. So my dv is going to be this quantity sin u du. So if you were to integrate, you get v is equal to negative times cos u. So integral u dv, that's going to be my u times dv is sin u du, and that is equal to uv. My u is capital U and my v is cos u, so it's going to be negative cos u. Of course I'm not going to touch the limits now. Let's hold the limits just for now, and then I will replace it. So minus integral negative positive cos u. Of course my du is just going to be this du. I hope you are able to follow what we are doing here. Because of this formula, I hope things don't get confused. So the limits are 0 to t, and the limits would be 0 to t and 0 to t. So if I were to substitute the upper limit, so it's going to be negative t times cos of t. I substitute the lower limit, this is going to be 0, right? Followed by integral of cos u will be sin u. Limits are 0 to t, so this is going to be negative t times cos of t, followed by sin t. So this is going to be 0. So this is what I have got. So we have to take this and substitute it here. So that's going to be negative t times cos t positive sin t. And in this case we will have to apply the limit. So this is Laplace transform of, so t times, I substitute the upper limit, is going to be negative cos t, substitute the lower limit, it's going to be negative of, there is already a negative sign here, this is going to become positive, negative of negative cos 0, that's going to be 1 there. So this sign can be taken out, so it's going to be positive. In fact I can bring the sign in and remove the parenthesis, so it's going to be positive t times cos t negative sin t. So this is what we have got. Now if I were to take the t inside, it's going to be negative t times cos t positive t times cos t negative sin t. Negative t times cos t positive t times cos t gets cancelled, giving me Laplace transform of t negative sin t. So this is what I have got. So now we will have to calculate the Laplace transform of this. So this is nothing but Laplace transform of t negative Laplace transform of sin t. Laplace transform of t is 1 over s squared, negative Laplace transform of sin t is 1 over s squared positive 1. If I were to take the LCM, s squared times s squared positive 1, this is going to give me s squared positive 1 negative s squared. S squared negative s squared gets cancelled, and that is going to be equal to 1 over s squared times s squared positive 1. So what is this exactly? This is nothing but the Laplace transform of the convoluted function f star g of t. But we know that the Laplace transform of the convoluted function f star g of t is equal to f of s times g of s. So we have only found out the left hand side, right? So we need to find out the right hand side. Okay, so consider Laplace transform of f of t. What is that? Laplace transform of f of t. Now if you were to go here, the Laplace transform of f of t, f of t is t, right? So which is nothing but, this is going to be Laplace transform of t, which is nothing but 1 over s squared, and we will consider Laplace transform of g of t. What is g of t? Sin t. So this is nothing but Laplace transform of sin t. What is that? That's going to be 1 over s squared positive 1. So hence Laplace transform of f of t times Laplace transform of g of t is equal to 1 over s squared times 1 over s squared positive 1, which is equal to 1 over s squared times s squared positive 1, right? So what is this exactly? You see this? This is what we add for the left hand side, and this is what we are getting for the right hand side. So if I were to take this as say 3, and if I were to take this as 2, from 2 and 3 we observe that we observe that the Laplace transform of f star g of t is equal to Laplace transform of f of t times Laplace transform of g of t. But what is this Laplace transform of f of t? F of s. What is this? This is nothing but g of s. So what do we conclude from here? This means hence the convolution theorem is verified, right? This is the exact essence of the convolution theorem. So we will move on to the next question. Students, we are given this question. The question wants us to find if Laplace transform of sin t times cos t is it equal to the Laplace transform of convolution of sin t with cos t. So let's do this. So first what I wish to do is I would like to take the right hand side. Consider the right hand side. So what have we got? We got the Laplace transform of convolution of sin t star cos t. Now we know that Laplace transform of convolution of f with g of t is equal to the Laplace transform of f of t times the Laplace transform of g of t. It is also rewritten, in fact you can also write this as capital F of s times g of s. So we know this. Now what we would do is hence Laplace transform of sin t convoluted with cos t is nothing but Laplace transform of sin t product Laplace transform of cos t. But what is Laplace transform of sin t? It's going to be 1 over s squared positive 1 squared, so we can write it as 1 times Laplace transform of cos t is s over s squared positive 1. So I can rewrite this as s over s squared positive 1 times s squared positive 1. So that's going to be s squared positive 1 raised to the power of 2. So what is this? This is nothing but Laplace transform of sin t convoluted with cos t. So this is what we have got. Now I'm going to say consider the left hand side. The left hand side is Laplace transform of sine t times cos t. So this is a product between sine and cos. A product is taking place. Okay. Now we know that. What do we know? We know that sine 2t is 2 times sine t cos t. So from here, this would mean my sine t times cos t is equal to 1 over 2 times sine 2t. So I can rewrite this as Laplace transform of 1 over 2 times sine 2t. This is a constant, take it out, 1 over 2 times Laplace transform of sine 2t. And this is nothing but 2 over s squared positive 2 squared, right? My 2 and 2 can be cancelled, giving me 1 over s squared positive 4. So if I were to take this as 2 and if I were to take this as 1, from 1 and 2 we conclude that the Laplace transform of sine t times cos t is not equal to the Laplace transform of sine t convoluted with cos t. So this is a nice handy result.
Welcome students, in today's class we will learn the initial value theorem. Now this theorem is very important for it has lot of practical applications. Now the basic concept is you are required, or I would say you are interested in finding the initial value of the function. So when we say initial value, it means starting value of a function, of any function for that matter. So having mentioned this, let us go on. So what is the statement? I would like to give you the statement of the initial value theorem. If the Laplace transform of f of t and f dash of t exists and Laplace transform of f of t is equal to f of s, then limit t tending to 0 of f of t is equal to limit s tending to infinity of s times f of s. So this is the required proof or formula that we would be interested in achieving. That is, if you are required to obtain the initial value of a function, then that initial value can be received by just finding the value of s times Laplace transform of the function as s tending to infinity. So that is the simplest way in which we can word it. So having mentioned this, let us look into the proof of this initial value theorem. Now let me just use this definition. We know that Laplace transform of f dash of t is equal to s times f of s negative f of 0. Right? We already know how to prove it, or in fact this is a popular result that we have been using. Now what I wish to do is I would like to take limit s tending to infinity. So with regard to this is just an s, right? So this s, this s, this s, they are all one and the same. So there's no change in signs there, or I would say there's no change in letters there. So I would be taking limits s tending to infinity on both sides. Say I would like to take this as 1 on both sides of 1. We get, so what do we get? This is going to be limit s tending to infinity of Laplace transform of f dash of t is equal to limit s tending to infinity of s times capital F of s negative f of 0. So fair enough. So I can rewrite this is actually infinity. I can rewrite this as limit s tending to infinity of s times f of s negative limit s tending to infinity of f of 0. On the left hand side, this is limit
s tending to infinity of Laplace transform of f of t. Now let me just show you. So if I were to take the Laplace transform of this, by definition this is nothing but integral 0 to infinity e raised to the power of negative st f of t times dt. We all know this definition, right? Now instead of f of t, we have f dash of t. So this can be rewritten as integral 0 to infinity e raised to the power of negative st f dash of t times dt. Now we know that the limits and the integral, they can be interchanged. So what I wish to do is I can easily bring the limit inside. So if I were to do that, this is going to be limit s tending to infinity of f dash of t times dt. Of course there is e raised to the power of negative st that's present there, and I'm going to place the limit outside, 0 to infinity outside. So on the right hand side, let me retain it as it is, limit s tending to infinity of s times f of s. Now over here, this limit is actually s tending to infinity, but this is f of 0. So the f that we see here is already given to be at f of 0. So we can just retain it as it is. Now I'm going to rewrite this left side as integral 0 to infinity. Let me write it like this, limit s tending to infinity of e raised to the power of negative st, right, times f dash of t times dt is equal to limit s tending to infinity of s times f of s negative f of 0. Now why did I write it like that? Because I can now be in a position to justify the outcome of this particular quantity, which is limit s tending to infinity e raised to the power of negative s times t. Now just observe here, as s tends to infinity, e raised to the power of negative st will tend to 0, right? Because it's negative here. So that would mean this entire thing will become 0. So this is going to give me 0 is equal to limit s tending to infinity of s times f of s negative f of 0. Now if I were to move this to the left, this would give me f of 0 is equal to limit s tending to infinity s times capital F of s. Now rewriting this, we get, so I'm going to rewrite this as limit s tending to infinity of s times f of s, and on the left this is f of 0, so I'm going to write this as limit t tending to 0 of f of t, right? So what do you see here? This is actually the initial value theorem. Hence the initial value theorem is proved. Students, now we will try to understand the final value theorem. I'm going to give you the statement and later on I will prove the final value theorem. So the statement is as follows: if the Laplace transforms of f of t and f dash of t exists, and that Laplace transform of f of t is equal to capital F of s, then the final value theorem states that limit t tending to infinity of f of t will be equal to limit s tending to 0 of s times f of s. So what is the understanding? The understanding is, if you want to get the final value of the function, all you need to do is find the value of the function s times f of s when s is tending to 0. So to prove this, let me use the definition. We know that by definition of Laplace transforms of derivatives, that Laplace transform of f dash of t is equal to s times Laplace transform of f of t negative f of 0, right? Now
I can rewrite this as s times f of s negative f of 0. So what we're going to do now is we are going to be taking limit s tending to 0 on both sides. So if we were to do that, this is going to be limit s tending to 0 of Laplace transform of f dash of t is equal to limit s tending to 0 of s times f of s negative f of 0. This is what we've got. Now we know that Laplace transform of f of t is integral 0 to infinity e raised to the power of negative st f of t times dt, right? This is from the definition. So what I would do is I would take this definition and place it for f dash of t. So if I were to take it as 1, therefore I can rewrite 1 as limit s tending to 0 of integral 0 to infinity e raised to the power of negative st f dash of t times dt. I'm going to rewrite this as limit s tending to 0 of s times f of s negative limit s tending to 0 of f of 0. Now I'm going to pull in the limit inside. So this is going to be limit s tending to 0 of e raised to the power of negative st. I'm going to write it like this. 0 to infinity f dash of t times dt is equal to limit s tending to 0 of s times f of s negative. Now this is limit s tending to 0 of f of 0. So that would give us just f of 0. Now as s is tending to 0, e raised to the power of negative st is going to be tending to 1. So this would mean I would now have integral 0 to infinity f dash of t times dt is equal to limit s tending to 0 of s times f of s negative f of 0. Now when you integrate f dash of t, you are going to get f of t, and the limits are 0 to infinity, and on the right side you're going to be getting limit s tending to 0 of s times f of s negative f of 0. Applying limits, we get f of infinity negative f of 0 is equal to limit s tending to 0 of s times f of s negative f of 0. Now negative f of 0 can be cancelled, giving you f of infinity is equal to limit s tending to 0 of s times f of s. Now you can rewrite this. Rewriting this, we can rewrite this as limit t tending to infinity of f of t is equal to limit s tending to 0 of s times f of s. Hence the final value theorem is proved. We are given this question: verify the initial value theorem and the final value theorem for the function f of t being equal to 1 positive e raised to the power of negative t of sine t positive cos t. Now first we will start off by verifying the initial value theorem. Okay, so this is going to be our solution, verifying the initial value theorem. So by definition we know that limit t tending to 0 of f of t is equal to limit s tending to infinity of s times f of s. So this is the definition of initial value theorem. Now we have been given f of t. So let us find the Laplace transform of f of t. Now that is equal to the Laplace transform of 1 positive, I'm going to write this as e raised to the power of negative t times sine t positive e raised to the power of negative t times cos t. Right?
Now this can be rewritten as Laplace transform of 1 positive Laplace transform of e raised to the power of negative t times sin t positive Laplace transform of e raised to the power of negative t cos t. Now Laplace transform of 1, we know that it's 1 over s plus, now we got Laplace transform of e raised to the power of negative t times sin t. So I'm going to first write the Laplace transform of sin t, which is 1 over s squared positive 1 with s, since I've got e raised to the power of negative t, by shift we would get s tending to s positive 1. Positive, we got Laplace transform of e raised to the power of negative t cos t. We know the Laplace transform of cos t is s divided by s squared positive 1 with the shift taking place because of the presence of e raised to the power of negative t. S is going to be tending towards s positive 1. In other words, I should say there is a shift from s to s positive 1. So this is equal to 1 over s positive 1 over s positive 1 raised to the power of 2 positive 1 positive s positive 1 over s positive 1 raised to the power of 2 positive 1. This is my Laplace transform of f of t. Now I need to evaluate this. So we have got, let me rewrite that down, Laplace transform of f of t being equal to 1 over s positive 2 divided by s squared positive 2s positive 2. Now how did I get this? Let me show that to you. We've got 1 over s positive 1 over s positive 1 raised to the power of 2 positive 1 positive s positive 1 over s positive 1 raised to the power of 2 positive 1. Now I would be taking the LCM as s positive 1 raised to the power of 2 positive 1 for these two terms. I'm not going to touch this term. So if I were to take the LCM as s positive 1 raised to the power of 2 positive 1, this is going to give me 1, followed by, this is going to give me s positive 1. Now this is equal to s positive 2 divided by s positive 1 raised to the power of 2 positive 1. That is exactly, if I were to expand this would be s positive 2 divided by s squared positive 2s positive 1 positive 1, which is s positive 2 divided by s squared positive 2s positive 2, which is what I have written here. And what is this? This is nothing but f of s, right? Now we are expected to verify the initial value theorem. So let me state that down. So IVT states as follows: limit t tending to 0 of f of t, we need to show that is equal to limit s tending to infinity of s times f of s. Now let me consider the left hand side. So we got limit t tending to 0 of f of t, which is equal to limit t tending to 0. What is f of t? F of t is given to be as 1 positive e raised to the power of negative t of sin t positive cos t. Now I would be rewriting this as limit t tending to 0 of 1 positive limit t tending to 0 of e raised to the power of negative t times sin t positive limit t tending to 0 of e raised to the power of negative t times cos t. Now t tending to 0 of e raised to the power of negative t times sin t, this is going to be 0, but this is a constant, so I retain it. This one would give me 1 because cos of 0 is 1, e raised to the power of negative of 0 is 1, so 1 multiplied by 1 will give me 1, so the outcome is going to be equal to 2. So let us rewrite this. So hence I have got limit t tending to 0 of f of t to be equal to 2. Now let us consider the right hand side. So what do we have on the right hand side? We got limit s tending to infinity of s times capital F of s, which is equal to limit s tending to infinity of s times my capital F of s. What is that? Let me show that to you. 1 over s positive s positive 2 divided by s squared positive 2s positive 2. This is what we've got. Now if I were to take s inside, this is going to be limit s tending to infinity of s over s positive limit s tending to infinity of s times s positive 2 divided by s squared positive 2 s positive 2. This is what we have got here. Now clearly s and s gets cancelled, you get 1, so s tending to infinity, this will produce 1. Now for this I would like to, probably I can just work it out right here. So limit s tending to infinity of, now I'm going to take a s out. I got a s here, I'm going to take a s out, so this is going to be 1 positive 2 over s. Right? Now I'm going to take s squared out, so this is going to be 1 positive 2 over s positive 2 over s squared. Now s squared and s squared gets cancelled, so I get positive limit s tending to infinity of 1 positive 2 over s divided by 1 positive 2 over s positive 2 over s squared. Now as s tending to infinity, 1 over s will tend to 0. So this is 0, this is 0, this is 0, you got 1 over 1. So this is going to be 1 positive 1, which is equal to 2. So if I were to take this as 3, if I were to take this as 2, clearly I can say from 2 and 3 we find that limit t tending to 0 of f of t is equal to limit s tending to infinity of s times f of s. Hence initial value theorem is verified. Right, that completes the solution for the first part of the question. We need to do the second part. Now let us go now for the final value theorem. Now what is the statement? We need to verify that the limit t tending to infinity of f of t is equal to limit s tending to 0 of s times of f of s. Now what I want to do is I would like to consider the left hand side, which is limit t tending to infinity of f of t. Now this is nothing but limit t tending to infinity. My f of t is given by 1 positive e raised to the power of negative t times sin t positive cos t. I would like to write that. So this is going to be 1 positive e raised to the power of negative t of sin t positive cos t. Now I can rewrite this as limit t tending to infinity of 1 positive limit t tending to infinity of e raised to the power of negative t of sin t positive cos t. Now this is a constant, so I can place it like that. Now t tending to infinity, so when t tends to infinity, e raised to the power of negative t will tend to 0. So you got a 0 product multiplied with the right hand side. So that is going to give me a value of 0, which is equal to 1. So I can state the output here. Hence we have limit t tending to infinity of f of t to be equal to 1. Now we will have to go to the right hand side. So now we will consider the right hand side. So what have we have got for the right hand side? We've got limit s tending to 0 of s times f capital F of s, which is nothing but limit s tending to 0 of s times, what is my capital F of s? We need to substitute that value. So let us go and check what we have got for capital F of s. So this is the value. Let me show that to you. This is the value we have got for capital F of s. So we would be substituting this. So let me do that. So this is s times of 1 over s positive 2 divided by s squared positive 2s positive 2. If I were to take s inside, this is going to be limit s tending to 0 of s times 1 over s positive s times of s positive 2 divided by s squared positive 2s positive 2. Now s and s can be cancelled, giving me limit s tending to 0 of 1 positive. I can take the limit inside. Limit s tending to 0 of no step s of s positive 2 s squared positive 2 times s positive 2. So this is what we have got. Now clearly you can see as s tends to 0, this entire thing, this is going to be 0 in the numerator, and in the denominator we got a 2. So when s is tending to 0, s times of s positive 2 divided by s squared positive 2s positive 2 will also tend to 0. So that means this is going to vanish and leaving us with a value of 1. What is on the left hand side? On the left hand side we've got limit s tending to 0 of s times f of s. Now if I were to take this as sum 4, and if I were to take this, maybe I should have taken this as sum 5, and maybe take this as sum 4. So what can we conclude? I'm going to write that down here. From 4 and 5 we observe that. So what is the observation? We see that limit t tending to infinity of f of t is equal to limit s tending to 0 of s times capital F of s. This means the final value theorem is verified, and hence the completion of this question. Students, we have given this question: verify the initial value theorem and the final value theorem for the function f of t being equal to 1 negative e raised to the power of negative 3t. So let me start off by stating the initial value theorem, which is limit t tending to 0 of f of t is equal to limit s tending to infinity of s times capital F of s. So foremost, what we will do is we will first consider the left hand side. Consider the left hand side, which is limit t tending to 0 of f of t. This is going to be limit t tending to 0. My f of t is 1 negative e raised to the power of negative s times t. Now when t is tending to 0, this quantity is going to become 1, and this has already got 1 there, so it's going to be 1 negative 1, which is equal to 0. So this means I now have found the value for f of t when t is tending to 0. So this implies f of t when t tends to 0 is 0. So this is one part. I would like to name it as 2. Now I will have to evaluate the second part. So I need to evaluate limit s tending to infinity of s times f of s, capital F of s. What is capital F of s? Capital F of s is nothing but Laplace transform of f of t. Now what is f of t given? It's 1 negative e raised to the power of negative 3 times t. I can rewrite this as Laplace transform of 1 negative Laplace transform of e raised to the power of negative 3t. Laplace transform of 1 is 1 over s. Laplace transform of e raised to the power of negative 3t is 1 over s positive 3. So this is going to be my Laplace transform of ft, which is also represented as capital F of s. So hence we are left to calculate limit s tending to infinity of s times capital F of s is equal to limit s tending to infinity of s times my capital F of s is found to be as 1 over s negative 1 over s positive 3. I can rewrite this as limit s tending to infinity. I can move s inside. I get s over s negative s over s positive 3. So this is what I've got. So I can cancel these two. That would give me limit s tending to infinity of 1 negative limit s tending to infinity of s over s positive 3. Now I can rewrite this s tending to infinity of 1, this is going to give me 1. So this is followed by limit s tending to infinity of, I can take a s out and that would give me 1 positive 3 over s. I can cancel these two and I can write this as 1 negative limit s tending to infinity of 1 over 1 positive 3 over s. Now as s tends to infinity, 1 over s, in fact it's 3 over s, in fact I can just simply say 1 over s. 1 over s will tend to 0, so that would mean this entire thing would give me 1. So this is going to be equal to 1 negative 1, which is equal to 0. So this would mean I now have limit s tending to infinity of s times f of s is equal to 0. Now the previous result I've named it as 2, I'm going to name this as 3. Clearly we can see that, clearly we observe that from 2 and 3 initial value theorem is verified. So that completes the first part of the solution. So students, we are left now to verify the final value theorem. Now final value theorem statement is as follows. So limit t tending to infinity of f of t is equal to limit s tending to 0 of s times capital F of s. If we can achieve this, then the final value theorem is verified. So foremost, what I will do is I will say consider the left hand side. The left hand side is limit t tending to infinity of f of t, which is nothing but limit t tending to infinity. My function f of t is given as 1 negative e raised to the power of negative t. Now let me rewrite this as limit t tending to infinity of 1 followed by a negative sign and limit t tending to infinity of e raised to the power of negative 3t. Now clearly this is going to be 1, but in this case I can clearly see as t is tending towards infinity, e raised to the power of negative 3t, this is going to be tending towards 0. So this would give me 0, so subsequently I will have the result as 1. So this implies limit t tending to infinity of f of t is equal to 1. So I can name this as sum 4 and then I can continue on. Okay, now consider the right hand side. Now we are considering the right hand side of the FVT. Okay, so I can state it over here. This is the left hand side of FVT. So the right hand side is limit s tending to 0 of s times of f of s. Now this is nothing but limit s tending to 0 of s times my capital F of s, that is given to be as 1 over s negative 1 over s positive 3. In fact, we found the value, right? We have actually found the capital F of s, right? I hope you can see the value, right? So we have already found that. So I'm just placing that value here. So this is equal to, I want to take s inside, so when I do that, limit s tending to 0 of s over s negative limit s tending to 0 of s over s positive 3. This one would give me 1, so I can write it as limit s tending to 0 of 1 followed by limit s tending to 0 of s over s of. Now this is going to be actually I was thinking we don't have to take s out, we can just simply retain it as s positive 3 because the limit is tending towards 0, it's not tending towards infinity. So if we are going to be applying limits, then this is going to be 1 followed by, now we have got s over s positive 3. Now this is tending towards 0, so in the numerator you get 0, in the denominator you get 0 positive 3, so that would mean you get 0 over 3 which is equal to 0, so this is going to be 0. So hence I can say from the evaluation limit s tending to 0 of s times f of s is equal to 1 negative 0 gives me 1, so this is equal to 1. So I've already taken this to be as 4. If I were to take it as 5, from 4 and 5 we observe that the final value theorem is verified. So this completes the solution to this question, students. Students, we are given this question: if L of f of t is equal to 1 over s times s positive va, find f of 0. Now they are actually asking us to find the initial value of the function. Now we are going to use the initial value theorem. So by IVT we know that, what do we know? We know that limit t tending to 0 of f of t is equal to limit s tending to infinity of s times capital F of s, right, where capital F of s is Laplace transform of f of t. From the question we know that Laplace transform of f of t is 1 over s times s positive a. So this means limit s tending to infinity of s times f of s is equal to limit s tending to infinity of s times f of s is 1 over s times of s positive a. Now s and s can be cancelled, giving me limit s tending to infinity of 1 over s positive a. As s tends to infinity, 1 over s tends to 0. This means 1 over s positive a will also tend to 0. So this is equal to 0. Now what does this mean? Okay, so this in turn would mean limit t tending to infinity, t tending to 0 of f of t will be equal to 0. This in turn would mean f of 0 is equal to 0. Hence the solution, because that is what they want us to find, right? So because they would want us to get the value of f of 0, and I've got the value of f of 0. So that's the solution, students. We'll move on to the next question. Students, we are given this question: if L of f of t is 1 over s times of s positive 1, we are expected to find the functional value when t tends to infinity. So what we are going to use is we are going to use the final value theorem. By FVT we know that, so what do we know? We know that limit t tending to infinity of f of t is equal to limit s tending to 0 of s times capital F of s, right? So this is equal to limit s tending to 0 of s times, my capital F of s is already given to be as 1 over s times of s positive 1. So clearly s and s can be cancelled, giving me limit s tending to 0 of 1 over s positive 1. Now when s is tending to 0, 1 over s positive 1 will tend to 1. So this is equal to 1. So what is the meaning of this? So this would mean the limit t tending to infinity of f of t is 1, and this we have achieved by final value theorem. So students, this completes our lesson on final value theorem and initial value theorem. We will meet again on our next topic. Thank you students, enjoy your night.